In the vast silence of the cosmos, where the light of a trillion stars weaves the fabric of our visible reality, there exist regions where light itself goes to die. These are the architects of galaxies, the destroyers of worlds, and the keepers of the universe's deepest secrets. Before we embark on this voyage into the darkness, we invite you to experience this journey in full screen, to immerse yourself completely in the void, and consider subscribing to join us for future explorations of the cosmos. Now, let the noise of the terrestrial world fade away as we drift upward, outward, and inward toward the event horizon of understanding. To understand the end of everything, we must first understand the beginning of force itself. The story of a black hole does not begin with darkness, but with the most fundamental interaction in the universe: gravity. It is the sculptor of the cosmos, a force that is at once ubiquitous and mysterious. In our daily lives, gravity is the gentle anchor that keeps our feet on the ground and the oceans in their beds. It is a constant, reliable presence defined by the mass of our home planet. But out in the deep vacuum of space, gravity reveals its true nature, not merely as a force of attraction between objects, but as the curvature of reality itself. We must discard the intuitive notion of gravity as an invisible tether pulling bodies together, and instead adopt the vision granted to us by Albert Einstein. Picture the universe not as a static stage where events play out, but as a dynamic, malleable fabric known as spacetime. This fabric is woven from the three dimensions of space and the fourth dimension of time, inextricably linked. Mass tells spacetime how to curve, and spacetime tells mass how to move. This elegant dance is the heartbeat of all celestial mechanics. Imagine a star, a colossal sphere of incandescent plasma suspended in this fabric. The sheer mass of the star creates a deep well in spacetime, a gravitational valley into which planets, asteroids, and light itself must traverse. For billions of years, a star is a battlefield of two opposing titanic forces. Inward pulls gravity, the relentless desire of all matter to collapse into a single point, to occupy the smallest possible volume. Outward pushes the explosive force of nuclear fusion, the process occurring in the stellar core where hydrogen atoms are crushed together to form helium, releasing photons and energy that exert immense pressure against the crushing weight of the star's own outer layers. This equilibrium, this hydrostatic balance, is what keeps a star alive. It is a fragile peace treaty written in the language of thermodynamics and gravitation. As long as the star has fuel to burn, the outward pressure holds gravity at bay, and the star shines, a beacon in the dark. But fuel is finite. The hydrogen reserves, however vast, eventually dwindle. When the fires of the core begin to flicker and fade, the treaty is broken, and gravity, patient and eternal, claims its victory. The death of a star is the birth of a black hole, but not all stars are granted this dark immortality. For a star like our Sun, the end is a relatively peaceful transition. When its fuel is exhausted, it will shed its outer layers to form a beautiful planetary nebula, leaving behind a white dwarf, a dense, cooling ember of carbon and oxygen, held up against gravity not by heat, but by the quantum mechanical pressure of electrons refusing to occupy the same state. This electron degeneracy pressure is a wall that gravity cannot breach for masses similar to our Sun, but nature has built darker rooms for those stars that live fast and die young, the massive giants that dwarf our own star in size and brilliance. For a star with a mass more than roughly 8 to 10 times that of the Sun, The end is violent and catastrophic. The core collapses with such speed and violence that the electron degeneracy pressure is shattered. Electrons are driven into protons to form neutrons, and for a brief moment, neutron degeneracy pressure halts the collapse. The shockwave of this sudden halt rebounds outward, tearing the star apart in a supernova explosion so bright it can outshine an entire galaxy. What remains is a neutron star, a city-sized sphere of matter so dense that a teaspoon would weigh 1 billion tons. Yet, there is a threshold beyond which even neutrons cannot stand against the crushing might of gravity. This limit, known as the Tolman-Oppenheimer-Volkoff limit, marks the boundary between the material and the abyss. If the remnant core of the supernova exceeds roughly 3 times the mass of our Sun, neutron degeneracy pressure fails. There is no force left in the known universe, no law of quantum mechanics or arrangement of particles that can halt the collapse. The core shrinks past the point of no return. It grows smaller and denser, until it occupies zero volume while retaining all its mass. The curvature of spacetime becomes infinite. The fabric of the universe is punctured. A singularity is born. Around this singularity lies a boundary, not of matter, but of consequence. This is the event horizon, the point of no return. It is the defining feature of a black hole, the invisible shell where the escape velocity required to break free exceeds the speed of light. Since the speed of light is the cosmic speed limit, the absolute ceiling for causality and information transfer in the universe, nothing that crosses this threshold can ever return. Not matter, not radiation, not information. Whatever passes the event horizon is severed from the observable universe forever, added to the mass of the singularity, lost to the dark. We call these stellar mass black holes the gravestones of massive stars. They are the most common type of black hole in the universe, drifting silently through the galactic disk. Though they are invisible to the naked eye, they are not undetectable. Their immense gravity betrays their presence. Often, a black hole is not alone. It is locked in a gravitational embrace with a companion star. As they orbit one another, the black hole strips gas from its partner. This stolen matter does not fall directly in. It carries angular momentum, causing it to swirl around the black hole in a flattened structure called an accretion disk. Friction within this disk heats the gas to millions of degrees, causing it to glow fiercely in X-rays. This is the paradox of the black hole. The darkest objects in the universe are often surrounded by the brightest lights. We see them not by looking at the void, but by looking at the scream of matter as it spirals to its doom. Cygnus X1, one of the first suspected black holes, was discovered this way. Located some 6,000 light-years from Earth, it is a potent X-ray source where a massive blue supergiant star is being slowly devoured by an invisible partner, roughly 15 times the mass of the Sun. Through the study of such binary systems, we have mapped the population of stellar graveyards in our own Milky Way, estimating that there may be hundreds of millions of these silent sentinels drifting among the stars. But the universe holds monsters far greater than these stellar remnants. If we journey from the spiral arms of our galaxy toward its chaotic, dust-choked center, we encounter a different class of darkness. Here, the stars are packed tightly together, moving at breakneck speeds, whipping around an invisible point in space. By tracking the orbits of these stars, specifically a group known as the S stars, over decades, Astronomers have calculated the mass of the object they orbit. It is not 10 times the mass of the Sun, nor 100. It is 4 million times the mass of our Sun, compressed into a region smaller than our solar system. This is Sagittarius A star, the supermassive black hole at the heart of the Milky Way. Unlike stellar black holes, the origins of supermassive black holes are shrouded in mystery. They are found at the center of nearly every large galaxy, anchoring the cosmic structure. Their masses can range from millions to billions of times that of the Sun. The sheer scale of these behemoths challenges our understanding of cosmic growth. Did they begin as stellar black holes and consume matter voraciously over billions of years? Did they form from the direct collapse of massive gas clouds in the early universe, bypassing the stellar stage entirely? Or are they the result of thousands of smaller black holes merging together in the chaotic density of forming galaxies? To understand the growth of such giants, we must look to the most energetic phenomena in the universe, quasars. A quasar is the blazing heart of a young, active galaxy, powered by a supermassive black hole feeding on a torrential influx of gas and dust. The accretion disk of a quasar is so luminous that it can outshine the combined light of all the stars in its host galaxy. These ancient beacons allow us to see back in time, to an era when the universe was younger and denser, and black holes were gorging themselves on the rich banquet of cosmic material. In the center of the galaxy M87, located 53 million light years away within the Virgo cluster, lies a monster far larger than our own Sagittarius A star. This supermassive black hole weighs in at 6.5 billion solar masses. It was this object that humanity first gazed upon directly. In April 2019, the Event Horizon Telescope, a planet-sized array of radio telescopes synchronizing their data with atomic clocks, captured the shadow of the black hole in M87. The image, a glowing orange ring of heated plasma surrounding a dark central void, was the first visual confirmation of Einstein's predictions in the strong gravity regime. It was not merely a photograph, it was a portrait of the absolute, a testament to human ingenuity and the unyielding laws of physics. The dark patch in the center was not the black hole itself, but the shadow cast by the event horizon against the backdrop of the glowing accretion disk, a silhouette of the unknown. Between the stellar mass remnants of individual stars and the supermassive titans anchoring galaxies, there lies a theoretical middle ground, intermediate mass black holes. These elusive objects, predicted to have masses between 100 and 100,000 suns, are the missing link in black hole evolution. If supermassive black holes grow from smaller seeds, we should see these adolescent stages scattered throughout the cosmos. Yet they remain notoriously difficult to find. They are too small to power the blinding luminosity of a quasar, and often too isolated to be caught feeding on a companion star. We hunt for them in the dense environments of globular clusters, ancient spherical cities of stars orbiting the galactic core. Here, in the crowded center, collisions and mergers might facilitate the growth of an intermediate mass black hole. Observational evidence remains tentative, often appearing as ultraluminous X-ray sources that are too bright for a standard stellar black hole, but not situated at a galactic center. Identifying and confirming these middleweights is crucial for understanding the hierarchy of black holes. They are the bridge across the mass gap, the evolutionary stepping stones that explain how the universe built its giants. Deeper still into the theoretical realm lies the concept of primordial black holes. These are not born of dying stars, they are children of the Big Bang itself. In the first fraction of a second of the universe's existence, the cosmos was a hot, dense soup of fundamental particles and energy. It was not perfectly uniform. Tiny quantum fluctuations created regions of slightly higher density. In some of these regions, the density may have been sufficient to cause direct collapse into a black hole. Primordial black holes could theoretically possess any mass, from the weight of a mountain compressed into the size of a proton to masses thousands of times that of the sun. They are ghosts of the creation event. Because they did not form from stars, they are not bound by the limits of stellar evolution. Some cosmologists propose that primordial black holes could constitute a portion, or perhaps all, of the mysterious dark matter that holds galaxies together. Dark matter exerts gravity but does not emit light, a description that fits black holes perfectly. If the universe is swarming with countless microscopic black holes, they would be virtually undetectable individually. Yet their collective mass would shape the large-scale structure of the cosmos. Searching for them involves looking for the subtle bending of light from background stars, gravitational microlensing, as these tiny, invisible objects pass in front of them. The nature of the black hole itself is defined by just three properties: mass, spin, and electric charge. This is the no-hair theorem, which states that all other information about the matter that formed the black hole is lost. Whether the black hole was made of hydrogen, iron, or antimatter, once it collapses, only these three numbers remain to describe it. In reality, we expect astrophysical black holes to have zero electric charge, as they would quickly attract oppositely charged particles from the surrounding medium to neutralize themselves. This leaves mass and spin as the two defining traits of the black holes we observe. Spin is a consequence of the conservation of angular momentum. Stars rotate, and when they collapse, that rotation accelerates. A rotating black hole, known as a Kerr black hole, is a far more complex beast than a stationary one. The rotation of the singularity drags the fabric of spacetime around with it, a phenomenon known as frame dragging. Around a spinning black hole, spacetime is twisted into a vortex. This region is called the ergosphere. Within the ergosphere, it is impossible to stand still. Space itself is moving faster than light relative to the distant universe. An object entering this region is forced to rotate in the direction of the black hole's spin. Theoretically, energy can be extracted from the ergosphere, tapping into the rotational energy of the black hole itself, a process proposed by physicist Roger Penrose. Let us return to the singularity, the heart of the mystery. In classical general relativity, the singularity is a point of infinite density where the laws of physics break down. It is a mathematical error message, a sign that our theory is incomplete. Infinite density and zero volume are impossible concepts in a quantum universe. This conflict between general relativity, which governs the macroscopic world of gravity, and quantum mechanics, which governs the microscopic world of particles, is the greatest unsolved problem in physics. Inside the black hole, these two great theories crash into each other. To understand what truly happens at the center, we need a theory of quantum gravity, a unification of Einstein and Planck. Until then, the interior of a black hole remains the province of speculation and advanced mathematics. Some theories suggest that the singularity is not a point, but a ring, in the case of rotating black holes, or that the collapse is halted by quantum effects, forming a dense core known as a Planck star. Others propose that black holes are gateways to other universes, or that our universe itself exists inside a black hole. The boundary of the black hole, the event horizon, is not a physical surface, but a mathematical location. Crossing it would be uneventful for a free-falling observer, at least initially. If the black hole is supermassive, the tidal forces at the horizon are weak. You could drift across the point of no return without realizing your fate was sealed. But as you fall closer to the singularity, the difference in gravitational pull between your feet and your head would grow extreme. You would be stretched vertically and compressed horizontally, a process vividly termed spaghettification. For a smaller, stellar mass black hole, these tidal forces are lethal even before you reach the horizon. You would be torn apart outside the black hole, your atoms added to the accretion disk. But for the giants, the horizon is a gentle threshold to oblivion. Once inside, all paths lead inward. Space and time swap roles. The radial distance to the singularity becomes a moment in time, the future. Just as you cannot stop the flow of time pushing you toward tomorrow inside a black hole, you cannot stop your motion toward the singularity. It is not a location you can avoid, it is an event that is going to happen. Yet, even black holes may not be eternal. In the 1970s, Stephen Hawking applied quantum field theory to the curved spacetime near an event horizon and made a startling discovery. The vacuum of space is not empty. It is seething with virtual particle pairs appearing and annihilating constantly. Near an event horizon, it is possible for one particle of a pair to fall in while the other escapes. To a distant observer, the escaping particle appears as radiation emitted by the black hole. This is Hawking radiation. The energy for this radiation comes from the mass of the black hole. Over unimaginable timescales, black holes slowly evaporate. They lose mass, shrink, and get hotter, eventually ending their lives in a burst of gamma rays. For astrophysical black holes, this process is agonizingly slow, far longer than the current age of the universe. But for tiny primordial black holes, evaporation could be rapid. This leads to the information paradox. If a black hole evaporates completely, what happens to the information about the matter that fell in? According to quantum mechanics, information cannot be destroyed. But if the black hole disappears, where did the record of its contents go? This paradox suggests we are missing a fundamental piece of the puzzle regarding how the universe stores its history. While the theoretical battles rage, observational astronomy has entered a golden age. We are no longer limited to seeing the universe in electromagnetic waves, light, X-rays, radio. We can now hear the universe through gravitational waves. When two black holes merge, they disturb the fabric of space-time so violently that ripples propagate outward at the speed of light. In 2015, the LIGO detectors picked up the signal of two black holes colliding over 1 billion light-years away. The signal, a chirp lasting a fraction of a second, carried more power than all the stars in the visible universe combined. This detection opened a new window on the cosmos. We can now detect invisible dark mergers, counting the population of black holes in the universe directly. We have seen black holes merging with neutron stars, and we are beginning to probe the population of intermediate mass black holes through these cataclysmic events. Gravitational wave astronomy allows us to probe the extreme gravity regime near the horizon, testing general relativity where the curvature is strongest. The role of black holes in cosmic evolution cannot be overstated. They are not merely destructive drains, they are engines of regulation. The energy released by matter falling into a supermassive black hole in the form of jets and radiation heats the surrounding gas of the galaxy. This heating can prevent the gas from cooling and collapsing to form new stars. In this way, the black hole controls the growth of its host galaxy. There is a tight correlation between the mass of the central black hole and the velocity dispersion of the stars in the galaxy's bulge, known as the M sigma relation. This suggests that the galaxy and its black hole grow in lockstep, influencing each other over billions of years. A galaxy is not just a collection of stars, it is an ecosystem regulated by the beating heart of its central singularity. The feedback from the black hole blows vast bubbles of hot gas into the intergalactic medium, redistributing heavy elements forged in stars, seeding the cosmos with the chemical ingredients for future solar systems and perhaps life. Consider the accretion disk in more detail. It is a maelstrom of magnetic fields and plasma. As matter spirals in, differential rotation winds up magnetic field lines like a spring. This magnetic tension can launch jets of particles at nearly the speed of light, shooting out from the poles of the black hole. These relativistic jets can punch through the galaxy and travel for millions of light years into deep space. They act as cosmic blowtorches, energizing the intergalactic medium. We see these jets in radio images of distant galaxies, vast lobes of emission dwarfing the visible galaxy itself. The physics of how a black hole launches these jets is still an area of active research involving the extraction of rotational energy from the black hole, the Blanford-Znajek process, or from the accretion disk, the Blanford-Payne process. It is a conversion of gravitational potential energy into kinetic energy on a galactic scale, the most efficient engine in the universe, far surpassing nuclear fusion. The photon sphere is another consequence of extreme gravity. At a specific distance from the black hole, 1.5 times the Schwarzschild radius for a non-rotating black hole, gravity is so strong that light photons are forced into circular orbits. If you were standing in the photon sphere looking horizontally, you would see the back of your own head. Light from the back of your head would circle the black hole and return to your eyes. The photon sphere is unstable. The slightest perturbation sends the photons spiraling inward to the horizon or outward to infinity. The ring of light seen in the EHT image of M87 corresponds to photons that have orbited the black hole multiple times before escaping to our telescopes. This photon ring is a fundamental prediction of relativity and a target for future, sharper observations. It is the closest we can visually get to the edge of the abyss. As we refine our models, we must consider the entropy of black holes. In thermodynamics, entropy is a measure of disorder or the number of possible microscopic configurations of a system. The physicist Jacob Bekenstein proposed that black holes have immense entropy, proportional to the surface area of their event horizon. This was a radical idea, linking geometry, area, with thermodynamics, entropy, and information theory. Hawking confirmed this with his radiation derivation. The Bekenstein-Hawking entropy formula is one of the few formulas in physics that includes the gravitational constant, g, the speed of light, c, Planck's constant, h, and Boltzmann's constant, k, uniting gravity, relativity, quantum mechanics, and thermodynamics. It suggests a deep connection between these disparate fields. It also leads to the holographic principle, the idea that the information of a three-dimensional volume, the interior of the black hole, can be encoded on a two-dimensional surface, the event horizon. Applied to the universe as a whole, this principle suggests that our three-dimensional reality might be a projection of information stored on a distant two-dimensional cosmic horizon. Let us journey back to the intermediate mass candidates. One of the strongest candidates is HLX1, hyperluminous X-ray source 1, in the galaxy ESO 243-49. Its X-ray luminosity and spectral characteristics strongly suggest a black hole of around 20,000 solar masses. It may be the stripped core of a dwarf galaxy that was cannibalized by the larger ESO 243-49. This supports the hierarchical merger model of structure formation. Big galaxies grow by eating small galaxies, and their black holes merge. The upcoming LISA mission, Laser Interferometer Space Antenna, will be a space-based gravitational wave detector capable of sensing the mergers of supermassive and intermediate mass black holes, frequencies too low for terrestrial detectors like LIGO. LISA will allow us to hear the gravitational symphony of the entire universe, detecting mergers from the dawn of time. The concept of the Schwarzschild radius is the cornerstone of black hole physics. It is the radius to which a mass must be compressed to become a black hole. For the Sun, this radius is about 3 kilometers. For Earth, it is about 9 millimeters, the size of a marble. The formula is deceptively simple. R equals 2 gm over c squared. It shows that black holes are not special because of what they are made of, but because of how dense they are. Anything can become a black hole if squeezed hard enough, but nature only provides the squeezing mechanism for massive stars. The density of a black hole decreases as its mass increases. A stellar mass black hole has a density far surpassing an atomic nucleus. But a supermassive black hole with billions of solar masses would have an average density lower than that of water. You could build a supermassive black hole out of air if you had enough of it. A sphere of air the size of the solar system would collapse under its own gravity to form a black hole. We must also consider the environment around the black hole, the innermost stable circular orbit, ISCO. For a non-spinning black hole, stable orbits for matter exist only down to 3 times the Schwarzschild radius. Inside this limit, no stable circular orbits are possible. Gas must plunge rapidly inward. This ISCO defines the inner edge of the accretion disk. For a rapidly spinning black hole, the ISCO moves closer to the event horizon, allowing matter to orbit just outside the point of no return. This proximity allows the gas to fall deeper into the gravitational well before disappearing, releasing more potential energy. Consequently, spinning black holes are more efficient engines, converting up to 42% of the infalling mass into energy, compared to roughly 6% for non-spinning ones. This efficiency explains the extreme luminosity of quasars. As we contemplate the future of the universe, black holes will be the last survivors. In the unimaginably distant future, long after the stars have burned out and galaxies have dissolved, the universe will enter the black hole era. Stars will cease to form. The cosmos will be a cold, dark expanse populated only by black holes and stray particles. But even these titans are mortal. Over timescales of Google years, 10 to the power of 100 years, the supermassive black holes will evaporate via Hawking radiation. As they shrink, they will glow faster and hotter, eventually detonating in the final fireworks of the universe. After the last black hole evaporates, the universe will enter a state of maximum entropy, a sea of photons and leptons cooling toward absolute zero. This heat death is the ultimate fate dictated by thermodynamics. But the journey of the black hole from stellar collapse to cosmic evaporation spans the entire history of time, linking the fiery beginning to the silent end. Our journey to all the black holes in the universe is a journey through the limits of our knowledge. From the smallest primordial fluctuations to the largest galactic hearts, these objects challenge our intuition and demand that we expand our understanding of physical laws. They are the laboratories where nature tests its most extreme theories. They are the sculptors of galaxies and the harbingers of doom. Yet, in their darkness, they illuminate the workings of the cosmos. By studying the invisible, we see the visible world more clearly. The study of black holes drives the development of new technologies, new mathematics, and new philosophies. It forces us to confront the boundaries of space, time, and information. As we continue to gaze into the abyss with our telescopes and detectors, we are not merely observing distant astrophysical objects. We are probing the fundamental architecture of reality itself. The black hole is the ultimate mirror, reflecting the deep structure of the universe back at us, waiting for us to decipher its distorted image. And so the exploration continues, driven by the insatiable human curiosity to know what lies beyond the horizon. Yet there is so much more to understand. So many layers deeper we must descend before the journey is complete. We have touched upon the fundamental physics, the categories of mass, the methods of observation. But the true depth of the black hole phenomenon extends into realms that challenge not just our instruments, but our capacity for conceptualization itself. To travel further along this path, we must return to the concept of space-time curvature and examine it with greater rigor, peeling back the simplifications to reveal the mathematical skeleton beneath. Einstein's field equations, which govern the behavior of spacetime in the presence of mass and energy, are 10 coupled, nonlinear partial differential equations. They are notoriously difficult to solve. In most scenarios, physicists rely on approximations or numerical simulations. But for certain idealized cases, exact solutions exist. The first and most famous is the Schwarzschild solution, derived by Carl Schwarzschild in 1916, mere months after Einstein published his general theory of relativity. Schwarzschild considered a perfectly spherical, non-rotating, uncharged mass in an otherwise empty universe. His solution described the geometry of space-time around such an object and revealed, for the first time, the mathematical existence of an event horizon. The Schwarzschild radius, denoted as RS, is the distance from the center of a non-rotating black hole to its event horizon. It is given by the formula Rs equals 2 times the gravitational constant times the mass of the black hole divided by the speed of light squared. For a black hole with the mass of our Sun, the Schwarzschild radius is roughly 3 kilometers. This means that if you could compress the entire mass of the Sun into a sphere smaller than 6 kilometers in diameter, it would become a black hole. The critical insight is that the Schwarzschild radius grows linearly with mass. A black hole with twice the mass has twice the Schwarzschild radius. For supermassive black holes, the event horizon can span millions or even billions of kilometers. Yet, despite this immense size, the black hole itself remains a singularity of infinite density at its core. The event horizon is not a physical surface. It is a mathematical boundary in spacetime. An object passing through the event horizon would experience no local disruption. The laws of physics remain continuous. The object simply crosses a threshold beyond which all future trajectories point inward. There is no escape, not because of a barrier, but because the structure of space-time itself has changed. The radial direction inward becomes time-like, and the future becomes the singularity. For rotating black holes, the situation becomes more complex and more intriguing. In 1963, Roy Kerr found an exact solution to Einstein's equations for a rotating black hole, now known as the Kerr metric. Rotation introduces angular momentum, and with it, a host of new phenomena. The Kerr black hole possesses not one but two event horizons, an outer and an inner horizon. Between these horizons lies a region called the ergosphere, a zone where space-time itself is dragged along with the rotation of the black hole. This frame-dragging effect means that no object, not even light, can remain stationary within the ergosphere. Everything is forced to co-rotate with the black hole, swept along by the current of spacetime. Yet, crucially, it is still possible to escape from the ergosphere, unlike from within the event horizon itself. This peculiar feature gives rise to a fascinating possibility known as the Penrose process. Named after physicist Roger Penrose, this process allows for the extraction of energy from a rotating black hole. If a particle falls into the ergosphere and splits into two fragments, one of which falls into the event horizon, while the other escapes, the escaping fragment can carry away more energy than the original particle possessed. This excess energy comes at the cost of the black hole's rotation. The black hole loses angular momentum, spins down slightly, and its mass energy decreases in accordance with the conservation of energy. In principle, advanced civilizations could harness this process to power their endeavors, drawing energy from the rotation of a black hole in much the same way we extract energy from rivers or wind. The structure of a Kerr black hole also includes an inner region known as the Cauchy horizon, beyond which the predictability of general relativity breaks down. The mathematics suggest that the interior of a rotating black hole might contain bizarre structures, including closed time-like curves, paths through spacetime that loop back on themselves, theoretically allowing travel into the past. Whether these solutions correspond to physical reality or are merely mathematical curiosities is unknown, as we have no way of observing the interior. The cosmic censorship conjecture, proposed by Penrose, suggests that nature abhors naked singularities, singularities not hidden behind an event horizon. If this conjecture holds, the strange inner structures of black holes remain forever isolated from the rest of the universe, incapable of influencing the external world. But the conjecture is unproven, and some solutions to Einstein's equations, such as those describing extremely rapidly rotating black holes, hint at the possibility of naked singularities under very specific conditions. This remains one of the open questions in theoretical physics, a frontier where the laws of causality and the consistency of spacetime hang in the balance. To deepen our understanding further, we must confront the nature of the singularity itself. In the classical description provided by general relativity, a singularity is a point where physical quantities such as density and curvature become infinite. The mathematics breaks down. General relativity, as elegant and powerful as it is a classical theory, meaning it does not account for quantum mechanics. Quantum mechanics governs the behavior of particles and fields at the smallest scales, introducing concepts such as uncertainty and discreteness. At the singularity, where the curvature of spacetime becomes extreme and the volume shrinks toward zero, quantum effects should dominate. Yet, we do not have a complete theory of quantum gravity, a framework that successfully unifies general relativity and quantum mechanics. String theory, loop quantum gravity, and other approaches have been proposed, but none have been experimentally verified. Without a quantum theory of gravity, we cannot accurately describe what happens at the singularity. It is possible that the singularity is not truly a point of infinite density, but rather a region where spacetime becomes quantized, structured at the Planck scale, a length scale of approximately 10 to the minus 35 meters, where the fabric of spacetime itself may be grainy or foamy, composed of discrete units rather than a smooth continuum. The concept of Hawking radiation brings quantum mechanics into the realm of black holes in a profound way. In 1974, Stephen Hawking calculated that black holes are not entirely black. Due to quantum fluctuations near the event horizon, particle-antiparticle pairs can spontaneously appear. Normally, these pairs annihilate each other almost immediately. However, near the event horizon, it is possible for one particle to fall into the black hole while the other escapes. To an outside observer, it appears as though the black hole is emitting radiation. This radiation carries energy away from the black hole, causing it to lose mass over time. The temperature of Hawking radiation is inversely proportional to the mass of the black hole. For stellar mass and supermassive black holes, this temperature is extraordinarily low, far colder than the cosmic microwave background radiation that permeates the universe. Thus, such black holes are actually gaining mass from the environment faster than they lose it through Hawking radiation. But for very small black holes, the temperature becomes extremely high. A black hole with the mass of a mountain would have a temperature of several billion degrees and would evaporate in a fraction of a second, releasing an immense burst of energy. If primordial black holes with very low masses exist, they would be evaporating right now, potentially detectable as sources of high-energy gamma rays. The evaporation of black holes through Hawking radiation introduces one of the most profound puzzles in modern physics, the black hole information paradox. According to quantum mechanics, information cannot be destroyed. The quantum state of a system evolves unitarily, meaning that if you know the state at one time, you can, in principle, reconstruct it at any other time. But when matter falls into a black hole, it appears to take its information with it. If the black hole then evaporates completely via Hawking radiation, and that radiation is purely thermal, meaning it contains no information about what fell in, then the information seems to vanish from the universe. This would violate the fundamental principles of quantum mechanics. Stephen Hawking initially argued that information is indeed lost, which would require a modification of quantum theory. But many physicists resisted this conclusion. Over decades of debate, it became clear that the paradox hinges on our understanding of the quantum nature of gravity. Recent work suggests that information is not lost, but is somehow encoded in subtle correlations in the outgoing Hawking radiation, or stored on the event horizon itself. This encoding might manifest in a way that's invisible to classical observers, but accessible through quantum calculations. The resolution of this paradox is still under active investigation and lies at the heart of attempts to construct a quantum theory of gravity. It is a problem where black holes serve as thought experiments, testing the consistency of our deepest physical theories. Let us consider the process of spaghettification more carefully, a phenomenon that awaits any object falling into a black hole. Gravity diminishes with distance according to an inverse square law. Near a black hole, the gradient of the gravitational field becomes extreme. If you were to fall feet first into a stellar mass black hole, the gravity pulling on your feet would be vastly stronger than the gravity pulling on your head. This difference, known as a tidal force, would stretch you vertically while compressing you horizontally. The word spaghettification is apt. You would be elongated into a thin strand. For a stellar mass black hole, these tidal forces become lethal well before you reach the event horizon. The difference in force across the length of your body would tear you apart at the molecular level. But here lies an interesting scale dependence. For a supermassive black hole, the event horizon is so large that the tidal forces at the horizon itself are relatively weak. You could cross the event horizon of a billion solar mass black hole without immediate discomfort, unaware that you had passed the point of no return. The tides would only become catastrophic as you approached the singularity deep inside. This counterintuitive fact arises because tidal forces depend not just on the strength of gravity, but on how rapidly it changes over distance. And that gradient is gentler for larger black holes. Time dilation near a black hole is another consequence of the warping of spacetime that deserves detailed examination. According to general relativity, clocks run slower in stronger gravitational fields. If you were to hover just above the event horizon of a black hole, time would pass extremely slowly for you compared to someone far away. If you remained there for what felt like an hour and then returned to distant space, you might find that centuries or millennia had passed for the outside universe. This effect is known as gravitational time dilation. At the event horizon itself, time dilation becomes infinite from the perspective of an outside observer. This means that if you watched someone fall into a black hole, you would never actually see them cross the horizon. You would see them slow down, redden, as the light from them becomes increasingly redshifted, and fade away, asymptotically approaching the horizon, but never quite reaching it. From your perspective, they are frozen at the edge. But from the perspective of the infalling person, nothing special happens at the horizon. They cross it in finite, proper time, experiencing no barrier or discontinuity. This discrepancy between perspectives is one of the most striking features of black hole physics. It highlights the observer-dependent nature of space-time events in relativity. We should turn our attention now to the observational techniques that have allowed humanity to detect and study these invisible entities. X-ray astronomy has been one of the most fruitful methods. When gas in an accretion disk is heated to millions of degrees by friction and compression, it emits X-rays. Space-based observatories such as NASA's Chandra X-ray Observatory and the European Space Agency's XMM Newton have cataloged thousands of X-ray sources, many of which are black holes in binary systems. The X-ray spectrum can reveal details about the temperature, density, and velocity of the accreting material. Rapid variability in the X-ray emission provides clues about the size of the emitting region, which can be as small as a few kilometers, consistent with the environment near a stellar black hole's event horizon. Iron emission lines in the X-ray spectrum are particularly diagnostic. The intense gravity near the black hole distorts these lines, broadening and skewing them in ways that reveal the velocity and trajectory of the emitting atoms. By analyzing these distorted spectral features, astronomers can measure the spin of the black hole and map the inner structure of the accretion disk. Radio astronomy complements X ray observations. The relativistic jets launched by black holes emit synchrotron radiation, which is strongest at radio wavelengths. Radio telescopes, both single dish and interferometric arrays, have mapped the morphology of these jets over vast scales. The Very Large Array in New Mexico, the Atacama Large Millimeter Array in Chile, and the Global Event Horizon Telescope collaboration have all contributed to our understanding of black hole environments. The EHT in particular represents a triumph of coordination and technology, linking radio dishes across the globe to create an Earth-sized virtual telescope. By observing at a wavelength of 1.3 millimeters, the EHT achieved an angular resolution sufficient to resolve the event horizon shadow of M87's black hole, a feat equivalent to reading a newspaper in New York from a cafe in Paris. Future upgrades to the EHT, including additional telescopes and space-based components, promise even sharper images, potentially allowing us to make movies of the swirling plasma around black holes and to observe the dynamic processes at the edge of oblivion in real time. Gravitational wave astronomy has opened a completely new window. The detection of gravitational waves from merging black holes by LIGO in 2015 confirmed a century-old prediction of general relativity and inaugurated the era of multi-messenger astronomy. Gravitational waves are ripples in spacetime itself, propagating at the speed of light. They are generated by the acceleration of massive objects, particularly in asymmetric configurations. When two black holes orbit each other, they emit gravitational waves, losing energy and spiraling inward. In the final moments before merger, the inspiral accelerates, and the waves grow in amplitude and frequency. The collision and merger produce a burst of gravitational radiation, and the resulting single black hole rings down, settling into a stable configuration. This entire process, from inspiral to merger to ring down, is imprinted in the gravitational waveform detected on Earth. By analyzing the waveform, scientists can determine the masses and spins of the original black holes, the mass and spin of the final black hole, and the distance to the system. Each detection adds a data point to the census of black holes, revealing the distribution of masses, the prevalence of binary systems, and the rate of mergers throughout cosmic history. The LIGO and Virgo collaborations have now detected dozens of black hole mergers, some involving black holes of unexpected masses. In 2020, LIGO detected the merger of a black hole with an object in the so-called mass gap between neutron stars and black holes, suggesting either an unusually massive neutron star or an unusually light black hole. In another event, a merger produced a black hole of approximately 150 solar masses, larger than what standard stellar evolution predicts for a single star, hinting at hierarchical mergers where black holes formed from previous mergers collide again. These discoveries challenge our models and force us to reconsider the pathways by which black holes form and grow. The upcoming generation of gravitational wave detectors, including LISA, the Einstein Telescope, and Cosmic Explorer, will extend our reach, detecting mergers at higher redshifts involving more massive black holes and with far greater sensitivity. These instruments will allow us to hear the gravitational hum of the entire universe, from the mergers of supermassive black holes at cosmic dawn to the inspiral of intermediate mass black holes in dense stellar clusters. Let us revisit the concept of the no-hair theorem in greater depth. The theorem states that a stationary black hole is completely characterized by only three externally observable parameters: mass, electric charge, and angular momentum. All other details about the matter that formed the black hole, its chemical composition, its structure, the arrangement of its particles, are erased. This is a profound statement about the loss of information in classical general relativity. It implies a kind of simplicity or elegance. Despite the chaotic violence of stellar collapse, the end product is described by just three numbers. But this simplicity is also troubling in the quantum context, as it seems to erase the information carried by the infalling matter. The no-hair theorem applies to classical black holes in a vacuum. When one includes quantum effects, the situation becomes more nuanced. Hawking radiation, though thermal in leading approximation, may carry subtle quantum correlations that encode information about the initial state. Some researchers propose that information is stored in the quantum structure of the horizon, perhaps in microscopic degrees of freedom that classical general relativity cannot see. Others suggest that information escapes through quantum tunneling or is preserved in correlations between the interior and exterior of the black hole. These ideas remain speculative and are areas of intense research. Resolving the tension between the no-hair theorem and quantum information conservation is central to developing a consistent theory of quantum gravity. The firewall paradox is a more recent twist on the information problem. In 2012, a group of physicists argued that if information is to be preserved and the Hawking radiation is to be non-thermal in a way that carries information, then the interior of the black hole must be highly energetic, a firewall at the horizon that would incinerate anything crossing it. This contradicts the equivalence principle, which states that an observer in free fall should experience no local effects as they cross the event horizon. The firewall paradox has sparked vigorous debate. Some propose modifications to the structure of spacetime near the horizon. Others suggest that the paradox reveals a flaw in our understanding of quantum entanglement across horizons. And still others argue that the assumptions leading to the paradox are too strong or rely on idealized conditions that do not hold in realistic astrophysical scenarios. The resolution remains elusive, but the debate has generated valuable insights into the interplay between quantum mechanics, general relativity, and thermodynamics. It demonstrates that black holes are not merely astrophysical objects, but theoretical laboratories where the limits of our current physics are tested and perhaps transcended. We must also address the observational challenges of detecting primordial black holes, if they exist. These objects, formed in the early universe, would not be surrounded by accretion disks or companion stars unless they happen to encounter matter. Isolated primordial black holes would be invisible, detectable only through their gravitational influence. One method is gravitational microlensing. If a primordial black hole passes between us and a distant star, its gravity will bend the star's light, causing a temporary brightening. Surveys such as EROS, MASHO, and OGLE have searched for such events. The results constrain the abundance of primordial black holes in certain mass ranges, but they do not rule them out entirely. Another approach is to look for the effects of Hawking radiation from very low-mass primordial black holes. If such objects exist and are evaporating, they would produce detectable signals in gamma rays or cosmic rays. So far, no definitive signal has been observed, placing limits on the population of evaporating black holes. Yet another method involves studying the cosmic microwave background and the large-scale structure of the universe. Primordial black holes would affect the formation of galaxies and the distribution of matter in subtle ways. By comparing observations with simulations, cosmologists can infer constraints on the contribution of primordial black holes to the total dark matter density. Each binary black hole systems offer unique opportunities for study. When two black holes orbit each other, the system loses energy through the emission of gravitational waves, causing the orbit to decay. This inspiral can take millions or billions of years, depending on the initial separation and masses. Eventually, the black holes merge. The final moments before merger are a crescendo of gravitational radiation, detectable across the universe. But before they merge, the black holes may interact with their environment. If they reside in the dense core of a galaxy or a star cluster, they can scatter stars and gas, creating a dynamic region of intense gravitational interactions. These interactions can either facilitate or hinder the merger. In dense environments, three-body interactions can extract energy from the binary, shrinking the orbit and accelerating the merger. In less dense environments, the binary may become stalled, unable to shed the remaining energy needed to coalesce. Understanding these dynamics is crucial for predicting the rate of black hole mergers and the properties of the signals we detect. Simulations of black hole binaries in galactic nuclei, globular clusters, and other environments are an active area of research in computational astrophysics. The role of magnetic fields in black hole accretion and jet formation deserves a deeper dive. Magnetic fields thread the plasma in the accretion disk. As the plasma spirals inward, it drags the magnetic field lines with it. Differential rotation winds up these field lines, amplifying the magnetic field strength. This process, known as the magnetorotational instability, generates turbulence in the disk, which in turn drives angular momentum transport outward and mass accretion inward. Without this mechanism, the gas would orbit the black hole indefinitely, unable to lose angular momentum and fall in. The amplified magnetic fields can also launch powerful jets. Near the black hole, the magnetic field lines are twisted into helical structures by the rotation of the spacetime, frame dragging. Charged particles are accelerated along these field lines to relativistic speeds. The exact mechanism is complex, involving the extraction of energy from the black hole's rotation or from the accretion flow itself. Magnetohydrodynamic simulations, which solve the equations governing the behavior of magnetized plasma in curved spacetime, have reproduced many of the observed features of jets, including their collimation, narrowness, and their ability to remain coherent over vast distances. These simulations are computationally demanding, requiring supercomputers to resolve the wide range of spatial and temporal scales involved. Now let us consider the fate of matter that falls into a black hole from the perspective of an infalling observer. As you approach the event horizon, you would not notice anything special locally. The laws of physics as you experience them remain the same. You would continue to fall, accelerating under gravity. But due to the curvature of spacetime, all your future light cones, the set of all possible future paths you could take, point inexorably inward. Once you cross the horizon, you cannot send a signal to the outside universe, because any signal you emit would also be trapped, destined to fall into the singularity. Your journey from the horizon to the singularity would be brief, measured in fractions of a second for a stellar mass black hole, or longer for a supermassive one. As you approach the singularity, tidal forces would grow without bound. The curvature of spacetime would become so extreme that the very atoms of your body would be torn apart, then the nuclei, then the quarks. At some point, the known laws of physics would cease to apply, and your fate would be determined by the quantum structure of spacetime, which we do not yet understand. In a sense, the singularity is the edge of the map, the point where our current theories admit their own limits. The concept of quasi-normal modes is important for understanding the ring-down phase after a black hole merger. When two black holes collide, the resulting black hole is initially distorted, not yet settled into the simple geometry described by the Kerr solution. It vibrates, much like a struck bell, emitting gravitational waves at specific frequencies and damping rates. These characteristic frequencies, called quasi-normal modes, depend only on the mass and spin of the final black hole. By measuring the frequencies and damping times in the gravitational wave signal, we can infer these properties. Moreover, quasi-normal modes provide a test of general relativity itself. Any deviation from the predicted frequencies would signal new physics, perhaps a modification of gravity at strong field regimes, or the existence of additional structure at the horizon. So far, all observations are consistent with general relativity, but the precision of measurements is improving with each detection. Future observations with more sensitive detectors will tighten these tests, potentially revealing cracks in Einstein's theory or confirming its validity in the most extreme conditions. The ergosphere and frame dragging around rotating black holes have fascinating implications. Frame dragging, predicted by general relativity and confirmed by experiments such as gravity probe B orbiting Earth, means that spacetime itself is set into rotation by a spinning mass. Near a rotating black hole, this effect becomes extreme. In the ergosphere, the region outside the event horizon where frame dragging is so strong that no object can remain stationary, it becomes possible to extract energy from the black hole through the Penrose process, as previously mentioned. Another mechanism for energy extraction is the Blandford-Znajek process, which involves magnetic fields threading the event horizon. The rotating black hole twists the magnetic field lines, which act like a dynamo, converting the rotational energy of the black hole into electromagnetic energy that powers the jets. This process is thought to be the engine behind some of the most luminous jets observed in quasars and blazars. Understanding the Blandford-Znajek mechanism requires combining general relativity with magnetohydrodynamics, a challenging theoretical and computational problem. Recent simulations have begun to capture the essential physics, showing how jets are launched, collimated, and accelerated to speeds approaching that of light. Let us turn to the observational evidence for black holes in our own galaxy. Beyond Sagittarius, a star, there are numerous X-ray binaries where stellar mass black holes are actively accreting from companion stars. V404 Cygni is one such system, a black hole of approximately 9 solar masses orbiting a low-mass companion star. It is known for its dramatic outbursts, during which the accretion rate increases suddenly, causing the X-ray luminosity to spike by factors of thousands. These outbursts provide snapshots of the accretion process in action. Another famous system is GRS 1915 plus 105, which hosts one of the most massive stellar black holes known, with estimates ranging from 10 to 18 solar masses. It exhibits complex variability patterns with oscillations and flares that challenge our models of accretion disk physics. By studying these systems in detail, astronomers can test theories of disk instability, magnetic field behavior, and the coupling between the disk and the black hole. The next generation of X-ray missions, such as the planned Athena Observatory, will provide spectroscopy with unprecedented resolution, allowing even finer probes of the inner accretion flow and the space-time geometry near the event horizon. The study of tidal disruption events offers another window into black hole physics. When a star passes too close to a black hole, the tidal forces can overcome the star's self-gravity, ripping it apart. Roughly half the stellar debris remains bound to the black hole and forms an accretion disk, while the other half is ejected. The sudden influx of gas causes a dramatic increase in luminosity, observable as a bright flare that can last for months or years. These events are relatively rare, occurring perhaps once every 10,000 years per galaxy. But modern surveys that monitor millions of galaxies have detected dozens of them. Tidal disruption events provide information about the mass and spin of the black hole, the properties of the disrupted star, and the dynamics of accretion onset. They are particularly valuable for studying otherwise quiescent black holes that are not actively feeding and would otherwise be invisible. Let us also explore the concept of black hole binaries in greater detail, particularly those detectable via gravitational waves. The population of black hole binaries reflects the history of star formation, stellar evolution, and dynamics in dense stellar environments. Some binaries form when two massive stars in a binary system both undergo supernova explosions, leaving behind two black holes bound to each other. Others form through dynamical capture in dense clusters, where black holes can sink to the center via dynamical friction and interact, forming binaries through three-body encounters. The properties of the detected binaries, masses, spins, orbital eccentricities, encode information about these formation channels. For example, binaries formed in isolation are expected to have low eccentricities by the time they enter the LIGO frequency band, because gravitational radiation circularizes the orbit. In contrast, binaries formed dynamically might retain some eccentricity. Spin alignment is another diagnostic. If the spins of the two black holes are aligned with each other and with the orbital angular momentum, it suggests they formed from a binary star system. If the spins are misaligned, it suggests a dynamical formation. By building a statistical sample of many detections, researchers are beginning to disentangle these formation channels and understand the demographics of black holes across cosmic time. The supermassive black holes at galactic centers have a co-evolutionary relationship with their host galaxies. Observations reveal tight correlations between the mass of the central black hole and properties of the galactic bulge, such as the bulge mass and the velocity dispersion of stars. These correlations suggest that the growth of the black hole and the formation of the galaxy are intimately linked. One proposed mechanism is feedback. As the black hole accretes and produces jets or winds, it heats the surrounding gas, preventing it from cooling and forming stars. This self-regulating process can explain why galaxies stop growing once they reach a certain size. It also explains the observed correlations. The black hole grows until its feedback becomes strong enough to halt further accretion and star formation, establishing a balance. This interplay between black holes and galaxies has profound implications for structure formation in the universe. Without black hole feedback, models predict that galaxies would be overly massive and would contain too many stars compared to what we observe. Including black hole physics in cosmological simulations improves agreement with observations, suggesting that these microscopic singularities play a macroscopic role in shaping the cosmos. The concept of a black hole as a one-way membrane is central to understanding its thermodynamics. The event horizon is a surface through which matter and energy can enter but never leave. This asymmetry is reminiscent of thermodynamic processes which have a preferred direction in time, from low entropy to high entropy. The connection between black holes and thermodynamics was formalized in the four laws of black hole mechanics, analogous to the laws of thermodynamics. The zeroth law states that the surface gravity, analogous to temperature, is constant over the event horizon of a stationary black hole. The first law relates changes in mass, area, and angular momentum, analogous to the first law of thermodynamics relating energy, entropy, and work. The second law states that the area of the event horizon never decreases in classical processes, analogous to the increase of entropy. The third law states that it is impossible to reduce the surface gravity to zero in a finite number of steps, analogous to the unattainability of absolute zero temperature. When Hawking discovered that black holes emit radiation, these analogies became physical identities. Black holes have a temperature, an entropy, and they radiate. This was a unification of gravity, quantum mechanics, and thermodynamics, hinting at a deeper underlying theory. We must consider the observational signature of black hole shadows in greater depth. The shadow is not the event horizon itself, but the region where light rays are captured by the black hole. Due to the bending of light, this shadow is larger than the event horizon by a factor that depends on the black hole's properties. For a non-rotating Schwarzschild black hole, the shadow radius is about 2.6 times the Schwarzschild radius. For a rotating Kerr black hole, the shadow is distorted, appearing smaller on the side that is rotating toward the observer and larger on the side rotating away due to relativistic effects. The shape and size of the shadow are direct probes of the space-time geometry near the horizon, providing tests of general relativity. The glowing ring seen in the EHT images is produced by light emitted from the accretion disk and bent by the black hole's gravity. Photons emitted from behind the black hole can be lensed around it and reach us, creating multiple images and a bright ring. The asymmetry in the brightness of the ring is due to Doppler beaming. Material moving toward us appears brighter, while material moving away appears dimmer. By measuring these asymmetries, we can infer the rotation of the accretion disk and, indirectly, the spin of the black hole. Let us travel now across the cosmic web to explore black holes in different galactic environments. In elliptical galaxies, which are old, spheroidal collections of stars with little gas and dust, the central supermassive black holes are often quiescent. They have consumed most of the available material and now lie dormant. Without fresh fuel, they do not emit powerful radiation. However, they remain massive and influential, shaping the motion of stars in the galactic nucleus through their gravity. In contrast, spiral galaxies like our Milky Way have ongoing star formation and reservoirs of gas, but their central black holes can still be relatively quiet. Sagittarius A star, as mentioned, accretes only a trickle of matter and is dim compared to its potential. But in starburst galaxies, where star formation proceeds at a frantic pace, the central black hole may also be highly active, fed by the turbulent gas flows generated by supernovae and stellar winds. The connection between star formation and black hole growth is complex and bidirectional. Black holes can regulate star formation through feedback, but star formation also provides the conditions for black hole feeding. Understanding this interplay requires detailed observations across the electromagnetic spectrum and sophisticated simulations that model the multi-scale physics of galaxies. Active galactic nuclei, or AGN, are galaxies with actively accreting supermassive black holes at their centers. They come in many flavors classified by their observational properties. Seyfert galaxies are relatively nearby AGN with prominent emission lines in their optical spectra. Radio galaxies emit strongly at radio wavelengths, often exhibiting large-scale jets and lobes. Quasars are the most luminous AGN, visible across cosmological distances. Blazars are AGN whose jets are pointed almost directly at us, causing their emission to be highly variable and beamed. The unified model of AGN proposes that these different types are manifestations of the same underlying phenomenon, a supermassive black hole with an accretion disk and jets, viewed from different angles and possibly at different stages of activity. The orientation of the accretion disk and the presence of obscuring material, such as a dusty torus surrounding the nucleus, determine what we observe. If we look edge-on through the torus, the nucleus is obscured, and we see only reflected or scattered light. If we look face-on, we see the bright accretion disk directly. If our line of sight is along the jet, we see a blazar. This unification has been remarkably successful in explaining the diversity of AGN, though the details continue to be refined as observations improve. We should examine the role of black holes in the formation and evolution of galaxies more carefully. In the early universe, shortly after the Big Bang, the first stars and galaxies began to form from the primordial hydrogen and helium. Some of the first stars were extremely massive, hundreds of times the mass of the Sun. When these behemoths died, they likely formed massive black holes. Alternatively, dense gas clouds in the early universe might have collapsed directly into black holes without forming stars first. These seed black holes then grew by accreting surrounding gas and by merging with other black holes during galaxy collisions. Over billions of years, through a combination of accretion and mergers, these seeds grew into the supermassive black holes we observe today. The rapid growth phase corresponds to the quasar era, roughly 10 to 12 billion years ago, when the universe was young and gas-rich. During this time, quasars were common, shining as the brightest objects in the cosmos. As the universe aged and galaxies depleted their gas reserves, the era of vigorous black hole growth came to an end. Today, most supermassive black holes are dormant or only mildly active, the fires of the quasar age long extinguished. Gravitational lensing provides another method to study black holes and the mass distribution in the universe. When light from a distant source passes near a massive object, the object's gravity bends the light, acting as a lens. This can magnify, distort, or create multiple images of the source. Galaxy clusters act as powerful gravitational lenses, bending the light of background galaxies into arcs and rings. Individual galaxies can also lens background quasars, creating multiple images separated by arcseconds. In rare cases, a star or a black hole within a lensing galaxy can cross the line of sight to a background source, causing a temporary brightening known as a microlensing event. By studying the time delays between images, the degree of magnification, and the shape of the distortions, astronomers can infer the mass and distribution of the lensing object. If a significant population of primordial black holes exists, they would contribute to the lensing signal. So far, lensing studies have constrained but not detected a dominant population of such black holes, though the search continues with ever more sensitive instruments. The environment of a black hole extends well beyond the event horizon. The accretion disk, as we have discussed, is a swirling maelstrom of gas and magnetic fields. But there are additional structures. Above and below the disk, in the polar regions, there may be a hot, tenuous corona of high-energy particles. This corona is thought to be responsible for the hard X-ray emission observed from many accreting black holes. The exact geometry and physical conditions of the corona are still debated, but it likely involves magnetic reconnection events, violent rearrangements of magnetic field lines that release energy and accelerate particles. Further out from the disk, there may be a broad line region where clouds of gas move at high speeds, producing broad emission lines in the spectrum. Even further out is the narrow line region, where the gas moves more slowly. These regions are observed in AGN and provide information about the velocity structure and ionization state of the gas around the black hole. By studying the spectrum and variability of the emission, astronomers can map these regions and understand the complex interplay between the black hole, the accretion flow, and the surrounding interstellar medium. Let us return to the question of how black holes spin. When a black hole forms from a collapsing star, it inherits the angular momentum of the star's core. Massive stars rotate, and when the core collapses, conservation of angular momentum causes it to spin faster, much like a figure skater pulling in their arms. The resulting black hole is born spinning. The dimensionless spin parameter ranges from 0, non-rotating, to 1, maximally rotating. For a maximally spinning black hole, the event horizon is located at the minimum possible radius, very close to the singularity, and the ergosphere extends furthest. As the black hole accretes matter, the angular momentum of the infalling material can either spin it up or spin it down, depending on the geometry of the accretion flow. If the accretion disk is aligned with the black hole's spin, accretion will generally increase the spin. If the disk is misaligned, or if the accretion is chaotic, the spin evolution is more complex. Measuring the spin of a black hole is challenging, but can be done through several techniques. One method involves analyzing the X-ray spectrum, particularly the shape of the iron emission line, which is distorted by the strong gravity and the motion of the gas near the event horizon. Another method uses the continuum spectrum of the accretion disk, which depends on how close the inner edge of the disk can get to the black hole, and thus on the spin. Gravitational wave observations of merging black holes also provide spin measurements, as the waveform encodes information about the spins of the progenitor black holes. The environments surrounding black holes are theaters of extreme physics, where temperatures soar to millions of degrees. Magnetic fields reach strengths trillions of times that of Earth, and matter moves at substantial fractions of the speed of light. To fully appreciate what occurs in these regions, we must examine the microphysics as well as the large-scale dynamics. At the microscopic level, the plasma in an accretion disk is a soup of ions and electrons threaded by magnetic fields. The ions, being more massive, carry most of the kinetic energy, while the electrons, being lighter and more mobile, generate the radiation through processes such as Bremsstrahlung, synchrotron emission, and inverse Compton scattering. Bremsstrahlung, or braking radiation, occurs when charged particles accelerate in the presence of other charged particles, emitting photons. Synchrotron radiation arises when electrons spiral around magnetic field lines at relativistic speeds, emitting beamed radiation. Inverse Compton scattering involves high energy electrons colliding with low energy photons and boosting them to higher energies, converting optical or infrared photons into X rays or gamma rays. These processes, operating simultaneously in the chaotic accretion environment, produce the complex spectra we observe. The magnetic dynamo mechanism in accretion disks is crucial for sustaining the magnetic fields that drive turbulence and jets. In a dynamo, kinetic energy from the differential rotation of the disk is converted into magnetic energy. Small-scale turbulence, driven by the magneto-rotational instability, stretches and twists the magnetic field lines, amplifying the field. This amplified field then exerts forces on the plasma, modifying the flow and feeding back into the turbulence. It is a self-sustaining cycle, a kind of cosmic engine that converts gravitational energy into magnetic energy, kinetic energy, and ultimately into radiation and jets. Understanding this process requires solving the equations of magnetohydrodynamics in the curved spacetime around the black hole, a formidable computational challenge that is only now becoming tractable with the advent of exascale supercomputers. Quasi-periodic oscillations, or QPOS, are another observational signature of black holes. These are periodic or quasi-periodic variations in the X-ray emission from an accreting black hole, with frequencies ranging from millihertz to kilohertz. QPOS are thought to arise from various physical mechanisms, such as precession of the inner accretion disk, oscillations of the disk itself, or the orbital motion of hot spots in the disk. By studying the frequency, amplitude, and harmonic structure of QPOS, astronomers can infer properties of the black hole and the accretion flow, including the mass, spin, and the location of the innermost stable orbit. QPOs are like the heartbeat of the accretion process, a rhythm that encodes information about the dynamics close to the event horizon. Let us consider the diversity of black holes across the universe in greater taxonomic detail. At the low mass end, we have the theoretical micro-black holes, objects with masses comparable to a mountain or less. If such objects exist, perhaps formed in the early universe or more speculatively in particle colliders, they would evaporate almost instantly through Hawking radiation. No observational evidence for micro-black holes has been found, and their existence remains speculative. Moving up the mass scale, we have stellar mass black holes formed from the collapse of massive stars, with masses typically between 5 and a few tens of solar masses. These are the most common black holes detected in X-ray binaries and through gravitational waves. Then there is the disputed mass gap, a range between about 50 and 100 solar masses where few black holes have been observed. The origin of this gap is unclear. It may relate to the physics of stellar explosions, where pair instability supernovae completely disrupt stars in this mass range, leaving no remnant, or it may be an observational bias. Recent gravitational wave detections have begun to populate this gap, suggesting that the gap may not be as empty as once thought. Intermediate mass black holes with masses between about 100 and 100,000 solar masses remain elusive but tantalizing. They are predicted to form through various channels: the collapse of extremely massive population 3 stars in the early universe, the direct collapse of dense star clusters, or the runaway merging of stars in the cores of young clusters. These objects, if they exist, could be the seeds from which supermassive black holes grow. Detecting them requires innovative observational strategies, such as searching for tidal disruption events in dwarf galaxies, looking for kinematic signatures in globular clusters, or using gravitational waves from intermediate mass black hole mergers. The discovery and characterization of a robust population of intermediate mass black holes would fill a critical gap in our understanding of black hole formation and evolution. Supermassive black holes with masses from 1 million to tens of billions of solar masses are the giants that anchor galaxies. Their formation remains one of the great unsolved problems in astrophysics. Did they grow from smaller seeds through accretion and mergers, or did they form through some more direct mechanism in the early universe? Observations of quasars at redshifts greater than 6, corresponding to times when the universe was less than 1 billion years old, reveal supermassive black holes with masses already reaching billions of solar masses. This poses a challenge. There may not have been enough time for a stellar mass black hole to grow to such a size through standard accretion, even at the maximum Eddington limited rate. Possible solutions include super Eddington accretion, where the black hole feeds faster than the Eddington limit would normally allow, or the formation of more massive seeds, such as intermediate mass black holes or direct collapse black holes formed from primordial gas clouds. Disentangling these scenarios requires detailed modeling and observations of the earliest black holes and their host galaxies. Ultramassive black holes, a term sometimes used for the very largest supermassive black holes with masses exceeding 10 billion solar masses, represent the extreme end of the spectrum. Examples include the black hole in the quasar TON 618, with an estimated mass of about 66 billion solar masses, and the black hole in the galaxy NGC 4889, estimated at around 21 billion solar masses. These behemoths are rare and represent the culmination of billions of years of growth. Their event horizons span distances larger than our entire solar system. Despite their immense size, they follow the same physics as their smaller cousins, governed by the curvature of space-time and the laws of thermodynamics. Studying these ultramassive black holes provides insights into the extremes of structure formation and the coevolution of galaxies and their central black holes over cosmic time. Primordial black holes, if they exist, would span a wide range of masses, limited only by the conditions in the early universe. Those with masses less than about 10 to the power of 15 grams would have evaporated by now through Hawking radiation. Primordial black holes in the mass range of asteroids or planets could still exist, contributing to dark matter or causing detectable lensing events. Those with stellar or larger masses would be indistinguishable from black holes formed later by stellar collapse or other mechanisms, except perhaps through their spatial distribution or clustering properties. Detecting a population of primordial black holes would be a major discovery, providing a window into the physics of the very early universe, including inflation, phase transitions, and the spectrum of primordial density fluctuations. We must also consider the concept of black hole remnants. In some quantum theories of gravity, the evaporation of a black hole via Hawking radiation does not continue all the way to zero mass. Instead, it leaves behind a tiny, stable remnant, a Planck mass relic that carries the information of everything that fell into the black hole. This would resolve the information paradox by providing a repository for the information, albeit in a form that is inaccessible with current technology. These remnants, if they exist, would be incredibly small and dense, and detecting them would be extraordinarily challenging. They might contribute to dark matter or produce subtle effects in particle physics experiments. The existence of remnants is speculative and depends on the details of quantum gravity, which remain unknown. But the possibility illustrates the range of ideas that physicists are exploring in their quest to understand black holes at the quantum level. The role of black holes in the Ryanization of the universe is another important topic. Ryanization is the process by which the neutral hydrogen gas that filled the universe after recombination was ionized, making the universe transparent to light. This occurred in the first billion years after the Big Bang. While the primary sources of ionizing radiation are thought to be the first stars and galaxies, accreting black holes, particularly quasars, may have contributed significantly. Quasars emit copious amounts of ultraviolet and X-ray radiation capable of ionizing hydrogen over vast volumes of space. The relative contribution of stars versus black holes to reionization is still debated and is an active area of research, combining observations from telescopes like the Hubble Space Telescope and the James Webb Space Telescope with sophisticated simulations of cosmic structure formation. As we contemplate the vast catalog of black holes across the observable universe, we must consider the statistical properties of black hole populations. The mass function of black holes, the distribution of their masses, tells us about formation mechanisms and evolutionary pathways. For stellar mass black holes detected through gravitational waves, we observe a preference for certain mass ranges, with a pileup around 8 to 15 solar masses and a potential gap around 50 to 150 solar masses. This mass distribution reflects the outcomes of stellar evolution, the physics of core collapse, and perhaps the metallicity of the progenitor stars. Lower metallicity stars, common in the early universe, may produce more massive black holes because they lose less mass through stellar winds. The spin distribution is also informative. High spins suggest formation from rapidly rotating stellar cores or growth through aligned accretion, while low or misaligned spins might indicate formation through mergers or chaotic accretion. For supermassive black holes, the mass function shows a range from 1 million to tens of billions of solar masses, with a peak around a few 100 million solar masses. This reflects the balance between black hole growth through accretion and mergers, and the availability of gas and the rate of galaxy mergers over cosmic time. The occupation fraction of black holes, what percentage of galaxies host a central supermassive black hole, is another key statistic. Observations suggest that nearly all massive galaxies contain a supermassive black hole at their center, while smaller galaxies and dwarf galaxies may or may not, depending on their formation history. The relationship between black hole mass and bulge mass is remarkably tight, suggesting a fundamental connection. This relationship, along with the observed quenching of star formation in massive galaxies, points to a co-evolutionary scenario where the black hole and the galaxy grow together, each influencing the other. The scatter in this relationship, the deviations from the average trend, may encode information about different growth histories, merger events, or environmental effects. By studying large samples of galaxies across a range of masses, redshifts, and environments, astronomers are piecing together the story of how black holes and galaxies have evolved together over the history of the universe. Let us now turn to the question of whether black holes could be used as energy sources. The idea of extracting energy from a black hole is not purely science fiction. As mentioned, the Penrose process allows energy extraction from the ergosphere of a rotating black hole. A more practical, though still highly speculative proposal involves a Dyson sphere around a black hole, capturing the energy radiated by its accretion disk. If matter is continually fed into the black hole, the accretion disk would shine with immense luminosity, and a sufficiently advanced civilization could harness this energy. Another concept is the black hole bomb. By surrounding a rotating black hole with a mirror that reflects certain frequencies of radiation, one could amplify waves extracted from the black hole's rotation through a process called superradiance. The waves bounce between the horizon and the mirror, extracting energy each time, growing in amplitude until they either escape or destabilize the system. These ideas are far beyond current technology, but they illustrate that black holes, despite being regions from which nothing can escape, paradoxically contain accessible energy in their rotation and accretion flows. The study of black holes also intersects with the search for quantum gravity. String theory, one of the leading candidates for a theory of quantum gravity, describes black holes as bound states of strings and branes. In string theory, the microscopic degrees of freedom of a black hole can be counted, at least for certain classes of black holes, yielding an entropy that matches the Bekenstein-Hawking formula. This is a remarkable success, providing a microscopic derivation of a macroscopic thermodynamic quantity. Loop quantum gravity, another approach, models spacetime as a network of quantized loops and applies these ideas to the interior of black holes. In loop quantum gravity, the singularity may be replaced by a quantum bounce, where the collapsing matter reaches a minimum volume and then re-expands, potentially creating a new region of spacetime on the other side. These are speculative ideas, but they demonstrate the rich interplay between black hole physics and quantum gravity, and the hope that black holes will provide clues to the ultimate theory. Analog black holes, or dumbholes, are laboratory systems that mimic certain properties of black holes. For example, a fluid flowing faster than the speed of sound in the fluid can create an acoustic horizon, beyond which sound waves cannot escape. These systems do not involve actual gravity or curved spacetime, but they obey analogous equations, and phenomena such as Hawking radiation have analogs in these systems. Researchers have created acoustic horizons in flowing water, Bose-Einstein condensates, and optical systems, and have observed signatures of analog Hawking radiation. While these systems are not true black holes, they provide a controlled environment in which to test ideas about horizons, quantum effects, and information loss, complementing purely theoretical work. The philosophical implications of black holes are profound. They confront us with limits to knowledge, to causality, to the very structure of reality. The event horizon is a boundary beyond which we cannot see, a cosmic censorship that hides the singularity from view. The singularity itself is a point where our laws break down, where the deterministic clockwork of physics grinds to a halt and gives way to uncertainty, or perhaps to something entirely new. Black holes challenge our notions of time. Inside the horizon, the roles of time and space are reversed in a sense. The singularity is not a place you go to, but a time you reach. The inevitability of the singularity once you cross the horizon is a temporal inevitability, not a spatial one. Black holes also challenge our understanding of information and reality. If information can be lost, then the past does not fully determine the future, and the universe is fundamentally non-deterministic in a way that goes beyond quantum uncertainty. If information is preserved, then reality must be more interconnected and holographic than our everyday experience suggests. Black holes also feature prominently in discussions of the ultimate fate of the universe. In the standard cosmological model, the universe is expanding and accelerating, driven by dark energy. Galaxies are receding from each other, and in the far future, most galaxies will disappear beyond the cosmic horizon, forever out of reach. Star formation will eventually cease as gas is exhausted. Stars will burn out, and the universe will be populated by white dwarfs, neutron stars, and black holes, along with planets, asteroids, and cold gas. Over unimaginably long timescales, even protons may decay if certain grand unified theories are correct, leaving only black holes and radiation. The black holes themselves will evaporate through Hawking radiation, the supermassive ones lasting the longest. After 10 to the power of 100 years or more, the last black holes will evaporate, and the universe will be a nearly empty expanse of photons, and perhaps a few stray particles, all redshifted and cooled to near absolute zero. This is the heat death, the maximization of entropy, the end of structure and complexity. Yet, even this bleak picture contains subtleties. If the universe continues to accelerate, the de Sitter horizon may also radiate, adding an additional layer of thermodynamics to the cosmos. The ultimate fate hinges on the nature of dark energy and the validity of our current understanding of cosmology, both of which remain uncertain. Returning to more immediate astrophysical concerns, we should examine the role of black holes in shaping the intergalactic medium, the diffuse gas that fills the space between galaxies. This gas is a significant reservoir of baryonic matter, containing more mass than all the stars in all the galaxies combined. The intergalactic medium is enriched with heavy elements produced in stars and expelled by supernovae and galactic winds. Black holes, through their jets and outflows, contribute to this enrichment and also to the heating of the intergalactic medium. The energy deposited by jets can prevent gas from cooling and collapsing to form new galaxies, a process that helps regulate the number density of galaxies and the overall structure of the cosmic web. Observations of the intergalactic medium using absorption line spectroscopy, where light from distant quasars passes through intervening gas clouds, imprinting absorption features, provide insights into the temperature, density, and chemical composition of this diffuse material, and by extension, into the feedback processes driven by black holes. We must also consider the role of black holes in galaxy mergers. When two galaxies collide, their central supermassive black holes are brought together. Initially, they sink toward the center of the newly merged galaxy through a process called dynamical friction, where their gravity stirs up the surrounding stars and gas, transferring energy and angular momentum. As they draw closer, the two black holes form a binary system. Gravitational interactions with surrounding stars can further shrink the orbit, but there is a potential bottleneck known as the final parsec problem. At separations of about a parsec, the binary may deplete the local stellar population, and further hardening of the orbit becomes inefficient. Gravitational waves eventually take over, driving the inspiral to coalescence, but this can take a very long time. The final parsec problem is an active area of research, with proposed solutions involving gas dynamics, triaxial stellar distributions, or third black holes that can perturb the binary. Observations of dual AGN, where two active black holes are seen in a single galaxy, and the detection of low-frequency gravitational waves will help resolve this issue. The merger of supermassive black holes is a key event in galaxy evolution, redistributing mass, expelling stars through gravitational slingshots, and potentially triggering bursts of star formation and AGN activity. The concept of recoil or kick velocity is important in the context of black hole mergers. When two black holes merge asymmetrically, if their spins or masses are not equal, the emission of gravitational waves has a preferred direction, imparting a net momentum to the system. This causes the final black hole to recoil, sometimes with velocities reaching thousands of kilometers per second. If the kick velocity exceeds the escape velocity of the host galaxy, the black hole can be ejected, becoming a wandering black hole in intergalactic space. Evidence for such recoiling black holes is tentative, with some quasars showing spatial offsets or velocity shifts suggestive of a recent kick. If common, recoiling black holes would have implications for the growth of supermassive black holes and the population of galaxies, as a galaxy that loses its central black hole would temporarily lack the feedback mechanism that regulates star formation. The frequency and magnitude of recoil kicks depend on the spins and orientations of the merging black holes, which are in turn influenced by the accretion history and the dynamics of the merger. Let us revisit the connection between black holes and gravitational waves in greater detail. Gravitational waves are perturbations in the metric of spacetime, traveling at the speed of light. They are generated by accelerating masses. But because gravity is weak, only the most extreme events produce detectable waves. Black hole mergers are ideal sources. The masses are large, the accelerations are immense, and the events are relatively common on cosmic scales. The waveform from a black hole merger encodes a wealth of information. The inspiral phase, where the two black holes spiral toward each other, produces a chirp signal, a wave that increases in frequency and amplitude as the black holes draw closer. The merger phase is a brief, violent collision, producing the peak amplitude. The ring-down phase is the newly formed black hole settling into a stable state, emitting gravitational waves at characteristic frequencies. By matching the detected waveform to templates generated from numerical relativity simulations, scientists can extract the masses, spins, distance, and even the inclination of the orbital plane. Deviations from the predicted waveforms could indicate new physics, such as modifications to general relativity, the presence of matter around the black holes, or exotic compact objects that are not black holes. The stochastic gravitational wave background is another target for detection. This is a diffuse background of gravitational waves from unresolved sources throughout the universe, analogous to the cosmic microwave background for electromagnetic radiation. The stochastic background could arise from the superposition of countless black hole mergers, from phase transitions in the early universe, from cosmic strings, or from other exotic sources. Pulsar timing arrays, which monitor the precise arrival times of pulses from millisecond pulsars, are sensitive to low-frequency gravitational waves and are currently searching for the stochastic background. Future space-based detectors like LISA will also probe this background. Detecting it would provide information about the population of black hole mergers across cosmic history and could reveal entirely new phenomena from the early universe. The electromagnetic counterparts to gravitational wave events are also of great interest. While black hole mergers are not expected to produce significant light, Because black holes themselves do not emit, the surrounding environment might. If the merging black holes are embedded in a disk of gas, the dynamics of the merger could disrupt the disk, causing flares or changes in the accretion rate. Searches for electromagnetic counterparts to LIGO events have so far yielded no confirmed detections from black hole mergers, but the search continues. In contrast, the merger of two neutron stars detected in GW 170817 produced a brilliant kilonova and was observed across the electromagnetic spectrum from gamma rays to radio waves. This event demonstrated the power of multi-messenger astronomy, where gravitational wave detections are combined with traditional telescope observations to gain a complete picture of the event. Black holes may also be implicated in the production of fast radio bursts, or FRBS, mysterious millisecond duration pulses of radio waves from distant galaxies. The origin of FRBs is still debated, with candidates including magnetars, highly magnetized neutron stars, supernova remnants, and interactions involving black holes. Some theories propose that FRBs are generated by the interaction of a black hole's magnetosphere with surrounding plasma, or by the collision of a black hole with a neutron star. The study of FRBs is a rapidly evolving field, with new detections and localizations providing clues. If black holes are responsible for some FRBs, this would add another observational signature to the black hole toolkit and potentially provide a way to detect otherwise invisible black holes in distant galaxies. The formation of the first black holes in the universe is a topic of great interest and active research. In the era shortly after the Big Bang, the first stars, known as population 3 stars, formed from primordial gas composed almost entirely of hydrogen and helium, with trace amounts of lithium. Without heavier elements to facilitate cooling, these stars were likely much more massive than stars forming today, perhaps hundreds of solar masses. When they exhausted their fuel and collapsed, they could have formed the first black holes. These initial black holes could then serve as seeds for the supermassive black holes we observe in the centers of galaxies today. Another possibility is the direct collapse of massive gas clouds into black holes without ever forming stars. In regions where the gas remains hot and does not fragment into stars, it could collapse directly to form a black hole of thousands or even tens of thousands of solar masses. Distinguishing between these scenarios requires observations of the earliest quasars and galaxies, as well as detailed simulations of structure formation in the early universe. Black holes also provide a natural explanation for the observed correlation between black hole mass and the properties of the galactic bulge. The most well-known is the m-sigma relation, which links the mass of the central black hole to the velocity dispersion of stars in the bulge. The tighter the correlation, the more fundamental the connection. This suggests that the growth of the black hole is intimately tied to the formation of the bulge. One possible mechanism is that both are fed by the same processes: gas inflows driven by galaxy mergers or disk instabilities. As gas flows toward the center, some of it forms stars in the bulge, and some accretes onto the black hole. The feedback from the black hole, in the form of jets and winds, can halt further inflows, establishing a self-regulated equilibrium. This coevolution explains why galaxies with more massive bulges also have more massive black holes. The exact physical mechanisms and the causal relationships are still under investigation, but the existence of these tight correlations is a key observational fact that any theory of galaxy formation must explain. Let us consider the observational prospects for detecting intermediate mass black holes in greater detail. These objects, if they exist, could reside in the centers of globular clusters, in the stripped nuclei of dwarf galaxies, or as isolated objects in the galactic halo. In globular clusters, the presence of an intermediate mass black hole would affect the dynamics of stars, causing a concentration of stars toward the center and a characteristic velocity dispersion profile. By measuring the motions of stars in the cluster, astronomers can infer the presence of a central mass. However, this is challenging because the clusters are far away, the stars are faint, and the expected effects are subtle. Another method is to look for tidal disruption events in dwarf galaxies. If a star wanders too close to an intermediate mass black hole, it would be torn apart, producing a flare of radiation. Surveys that monitor many galaxies for transient events are beginning to find candidates. Gravitational waves are perhaps the most promising method. The inspiral and merger of intermediate mass black holes would produce gravitational waves at frequencies accessible to future detectors like LISA. Detecting such events would not only confirm the existence of intermediate mass black holes, but also provide precise measurements of their masses and spins. The relationship between black holes and quasars deserves further exploration. Quasars are the most luminous, persistent objects in the universe, powered by supermassive black holes accreting at prodigious rates. At their peak, roughly 10 billion years ago, quasars were common, marking an era of intense black hole growth. The light from quasars allows us to study the conditions in the early universe. Absorption lines in quasar spectra caused by intervening gas clouds map the distribution of matter along the line of sight. The Lyman alpha forest, a series of absorption lines due to neutral hydrogen, traces the cosmic web of filaments and voids. Quasars also serve as lighthouses, probing the ionization epoch when the first stars and black holes ionized the intergalactic medium. The spectra of the most distant quasars show regions where the light is completely absorbed, indicating patches of neutral hydrogen that have not yet been ionized. By studying these spectra, cosmologists piece together the timeline of reionization and the role of black holes in this transformative phase of cosmic history. Black holes also feature in discussions of the anthropic principle and the fine-tuning of the universe. The properties of black holes depend on fundamental constants such as the gravitational constant, the speed of light, and Planck's constant. If these constants were slightly different, black holes might not form, or they might dominate the universe, preventing the formation of stars and galaxies. The fact that our universe has the constants it does, allowing for a rich variety of structures including stars, planets, and life, has led some to speculate about the anthropic principle. We observe these constants because only in a universe with these constants could observers like us exist. Black holes, as extreme manifestations of gravity and spacetime, sit at the boundary of what the universe allows. Their existence and properties are a testament to the delicate balance of forces and constants that shape reality. The exotic interiors of black holes have also inspired speculations about connections to other universes or other regions of spacetime. The Einstein-Rosen bridge, a mathematical solution describing a wormhole connecting two regions of spacetime, emerges from the equations of general relativity. However, such wormholes are not traversable in the classical theory. They collapse too quickly for anything to pass through. To keep a wormhole open would require exotic matter with negative energy density, which violates classical energy conditions. Quantum field theory allows for temporary violations of these conditions, leading to speculations about quantum stabilized wormholes. Even more speculatively, some theories propose that the interior of a black hole could connect to a white hole in another universe, with matter that falls into the black hole eventually emerging from the white hole. These ideas are highly speculative and currently untestable, but they illustrate the richness of general relativity and the imaginative leaps that black holes inspire. Let us also discuss the role of black holes in testing the equivalence principle, one of the foundational pillars of general relativity. The equivalence principle states that gravitational and inertial mass are identical, and that the effects of gravity are locally indistinguishable from acceleration. This principle implies that all objects, regardless of their composition, fall at the same rate in a gravitational field. While the equivalence principle has been tested to high precision in the solar system, black holes provide a much more extreme testing ground. By observing the orbits of stars or the trajectories of photons near a black hole and comparing them to the predictions of general relativity, we can test whether the equivalence principle holds in strong gravitational fields. Any deviation would be groundbreaking, suggesting new physics beyond Einstein's theory. So far, no such deviations have been detected, reinforcing the validity of general relativity, even in the most extreme environments. The numerical simulation of black holes and their environments is a major computational challenge and achievement. Simulating the merger of two black holes in general relativity requires solving Einstein's field equations in a dynamic, nonlinear regime. This was not possible until the mid-2000s, when breakthroughs in numerical relativity allowed stable, long-term simulations. These simulations showed that black holes can indeed merge, radiating away a significant fraction of their mass as gravitational waves, and that the final black hole settles into a Kerr black hole. Simulating the accretion disk and jets requires solving the equations of magnetohydrodynamics in curved spacetime, accounting for the plasma physics, radiation transfer, and the back reaction of the matter on the spacetime. These simulations are computationally intensive, often requiring months of runtime on supercomputers. They produce synthetic observations, what a telescope would see if pointed at the simulation, that can be compared directly to real observations, allowing theorists to test and refine their models. The interplay between simulation and observation is driving rapid progress in our understanding of black holes. We must also consider the implications of black holes for the arrow of time. The second law of thermodynamics states that entropy increases over time, giving time a direction. Black holes, with their immense entropy, are intimately connected to this law. When matter falls into a black hole, the total entropy of the universe increases, even if the matter itself was in a low entropy state. This irreversible increase in entropy contributes to the arrow of time. Hawking radiation introduces a wrinkle. If black holes evaporate, the information and entropy are eventually returned to the universe, albeit in a scrambled form. The process of black hole formation, growth, and evaporation is a cycle that spans the entire age of the universe and beyond, a cosmic process that embodies the thermodynamic arrow of time. The study of black hole thermodynamics thus connects to deep questions about the nature of time, the origin of the second law, and the ultimate fate of information in the universe. Black holes also play a role in the production and distribution of cosmic rays, high-energy particles that constantly bombard Earth from space. Cosmic rays consist mostly of protons and atomic nuclei, traveling at nearly the speed of light. The sources of the highest energy cosmic rays are unknown, but black holes, particularly the jets from active galactic nuclei, are prime candidates. In the acceleration regions of jets, particles can gain energy through processes such as shock acceleration or magnetic reconnection. These accelerated particles, upon escaping the jet, become cosmic rays that propagate through the intergalactic and interstellar medium. Observations of a cosmic ray spectra, arrival directions, and composition are used to constrain models of their origin. Linking specific cosmic rays to their sources is difficult because magnetic fields in space deflect the charged particles, scrambling their trajectories. Nonetheless, correlations between the arrival directions of the highest energy cosmic rays and the positions of nearby active galactic nuclei have been tentatively observed, suggesting a connection. Let us return to the theme of testing general relativity with black holes. The theory has been tested in the weak field regime, such as the precession of Mercury's orbit, the bending of starlight by the sun, and the time delay of radar signals passing near the sun, with exquisite precision. But black holes provide tests in the strong field regime, where the curvature of spacetime is extreme, and deviations from general relativity, if they exist, would be most apparent. The shape of the black hole shadow, the spectrum of gravitational waves from mergers, the orbits of stars around Sagittarius A star, and the precession of accretion disk features all provide opportunities to test the theory. So far, general relativity has passed every test. The shadow of M87 matches the predictions. The gravitational waveforms from LIGO are consistent with the theory, and the motion of stars around our galactic center follows the expected geodesics. Yet the search for deviations continues, driven by the knowledge that general relativity is incomplete. It must break down its singularities, and it does not incorporate quantum mechanics. Finding where and how it deviates would point the way to a more complete theory. The phenomenon of gravitational lensing by black holes is also worth examining in detail. When light passes close to a black hole, the black hole's gravity bends the light path, acting as a lens. If a luminous object is located behind a black hole from our perspective, the black hole can magnify, distort, or create multiple images of that object. For a perfectly aligned system, the light from the background object forms a ring around the black hole, called an Einstein ring. More generally, the images are arcs or distorted shapes. The degree of distortion and the separation of the images depend on the mass of the black hole, the distances involved, and the alignment. Gravitational lensing is not unique to black holes. Any massive object can lens light, but black holes, due to their compactness and the strong curvature they produce, create particularly dramatic lensing effects. In principle, if a stellar mass black hole were to pass directly between Earth and a background star, it would cause the star to brighten and create a lensing pattern that could reveal the presence of the black hole. Such events are rare, but large-scale surveys monitoring millions of stars increase the chances of detection. Let us also consider the observational evidence for black holes from stellar kinematics. By tracking the motion of stars orbiting an invisible object, astronomers can infer the object's mass, and if the mass is high enough and the volume small enough, conclude that it must be a black hole. The most famous example is the study of S stars orbiting Sagittarius A star. Over more than 2 decades, astronomers have measured the precise orbits of these stars, some of which come within a few light hours of the black hole, traveling at several percent of the speed of light. The orbits are consistent with Keplerian motion around a point mass of about 4 million solar masses, confined to a region smaller than the orbit of Mercury around the Sun. No configuration of normal matter could be so compact and yet stable. The conclusion is inescapable. Sagittarius A star is a supermassive black hole. Similar studies in other galaxies, though less detailed due to the greater distances, have confirmed the presence of central black holes in most large galaxies. The structure of spacetime around a rotating black hole is described by the Kerr metric, which we have mentioned but not fully explored. The Kerr solution introduces a new feature, the dragging of inertial frames. In flat spacetime, an inertial reference frame is one that is not accelerating. But near a rotating black hole, spacetime itself is rotating, and an inertial frame must rotate along with it. This means that a stationary observer, one who hovers at a fixed position relative to the black hole, must fire rockets to resist being dragged along with the spacetime flow. Inside the ergosphere, even rockets cannot keep you stationary. You are forced to co-rotate. This frame dragging effect has been measured around Earth, which rotates and thus drags spacetime slightly, an effect detected by the Gravity Probe B satellite. Around a black hole, the effect is vastly magnified, dominating the structure of spacetime close to the horizon. The innermost stable circular orbit, or ISCO, is a critical concept in accretion disk theory. For a non-rotating Schwarzschild black hole, the ISCO is at 3 times the Schwarzschild radius, or 6 gravitational radii. Inside this radius, orbits are unstable. Any perturbation causes the orbiting matter to spiral inward or outward. For a rotating black hole, the ISCO depends on the spin and the direction of the orbit. For prograde orbits, aligned with the black hole's spin, the ISCO can be as close as 1 gravitational radius for a maximally spinning black hole. For retrograde orbits, it is farther out at 9 gravitational radii. This difference affects the efficiency of energy extraction. Matter in a prograde orbit can fall deeper into the potential well before plunging into the black hole, releasing more gravitational energy. This is why rapidly spinning black holes are associated with the most luminous accretion disks and powerful jets. Measuring the location of the ISCO through X-ray spectroscopy or timing provides a direct measurement of the black hole's spin. The concept of a horizon in general relativity is more subtle than it might appear. The event horizon is a global concept defined by the causal structure of the entire spacetime. It is the boundary of the region from which no future-directed time-like or null curve can reach infinity. Determining the location of the event horizon requires knowledge of the entire future evolution of the spacetime. In contrast, an apparent horizon is a local concept, defined at a given moment in time as the boundary of trapped surfaces. Surfaces where all outgoing light rays are converging. For a stationary black hole, the event horizon and the apparent horizon coincide. But in dynamical situations, such as a black hole merger or a collapsing star, they can differ. Numerical relativists often work with apparent horizons because they can be calculated from data on a spatial slice without needing to know the future. The study of horizons, their properties, and their evolution is a rich area of mathematical general relativity, with implications for black hole thermodynamics and quantum gravity. Black holes can also be characterized by their surface gravity, which is not the same as the tidal force or the acceleration experienced by an observer far away. Surface gravity is a measure of how rapidly an observer must accelerate to remain stationary just above the horizon. For a Schwarzschild black hole, the surface gravity is inversely proportional to the mass. Larger black holes have lower surface gravity. In fact, for a supermassive black hole, the surface gravity at the horizon is quite weak, comparable to the surface gravity on Earth. This might seem paradoxical. After all, the black hole's gravity is immense, but it reflects the fact that the horizon is very far from the singularity in geometric terms, and the curvature at the horizon, while significant, is not infinite. Surface gravity is directly related to the Hawking temperature. The temperature of the black hole is proportional to its surface gravity. This connection between a geometric quantity and a thermodynamic quantity is one of the deep insights of black hole physics. We should also examine the concept of black hole complementarity, a principle proposed to address the information paradox and the firewall problem. Complementarity suggests that different observers can have different but complementary descriptions of the same physics, without contradiction, because they cannot communicate their observations to each other. An observer falling into a black hole sees nothing unusual at the horizon and continues smoothly to the singularity, experiencing the interior of the black hole. An observer remaining outside never sees the infalling observer cross the horizon, and from their perspective, the information is eventually released in Hawking radiation. Both descriptions are valid within their respective reference frames, but they cannot be directly compared because the observers cannot share their observations once one has crossed the horizon. This idea is inspired by similar principles in quantum mechanics, such as the complementarity between position and momentum. However, black hole complementarity is controversial and not universally accepted. It requires a radical rethinking of how information and causality work in the presence of horizons. The question of what lies beyond the event horizon is one that science may never be able to answer empirically, because by definition, no information can escape from inside to tell us. Any probe sent in would be lost, its data irretrievable. This fundamental limitation makes the interior of a black hole one of the ultimate frontiers of theoretical physics, accessible only through mathematical reasoning and the extrapolation of physical laws into extreme regimes. Some theorists speculate that the singularity might be avoided in a full quantum theory of gravity, replaced by a region of high but finite curvature, or by exotic structures such as bouncing geometries or connections to other regions of spacetime, so-called wormholes or Einstein-Rosen bridges. However, these ideas remain speculative. The classical singularity theorems of Hawking and Penrose show that, under very general conditions, singularities are inevitable in general relativity. Avoiding them requires new physics beyond general relativity. Let us consider the timescale for black hole evaporation more carefully. The lifetime of a black hole due to Hawking radiation is proportional to the cube of its mass. For a solar mass black hole, the evaporation time is on the order of 10 to the power of 67 years, vastly longer than the current age of the universe, which is about 10 to the power of 10 years. For a supermassive black hole with 1 billion solar masses, the evaporation time is 10 to the power of 100 years or more. These timescales are so immense that they are almost beyond comprehension. In the far, far future, long after the stars have died and the universe has cooled, black holes will slowly radiate away, growing hotter and smaller as they do. The final moments of a black hole's life would be spectacular. As the mass drops, the temperature skyrockets, and the black hole would radiate intensely, eventually exploding in a burst of high-energy particles and radiation. This final explosion would release the last vestiges of the black hole's mass energy, leaving behind only photons and particles that disperse into the void. Whether anything, such as a Planck-scale remnant, survives this explosion is unknown. The thermodynamic properties of black holes have led to the development of black hole mechanics, a set of laws analogous to the laws of thermodynamics. The Zeroth law states that the surface gravity is constant over the horizon of a stationary black hole, analogous to the temperature being constant in thermal equilibrium. The first law relates the change in mass, energy of a black hole to changes in its area, entropy, angular momentum, and charge, analogous to the first law of thermodynamics. The second law states that the total area of all horizons never decreases in any classical process, analogous to the second law of thermodynamics that entropy never decreases. The third law states that one cannot reduce the surface gravity to zero, analogous to the third law that one cannot reach absolute zero temperature. These analogies were initially formal, but with Hawking's discovery that black holes radiate, they became physical laws. Black holes truly have a temperature and entropy. This has profound implications. It suggests that the laws of thermodynamics are not merely emergent properties of matter, but are deeply connected to the structure of space-time itself. The entropy of a black hole is proportional to the area of its event horizon, not its volume. This is surprising because entropy typically scales with volume. The number of microstates available to a system usually grows with the volume of the system. The fact that black hole entropy scales with area suggests that the fundamental degrees of freedom are somehow located on the horizon rather than in the interior. This observation is the basis of the holographic principle, which proposes that all the information contained within a volume of space can be represented as a theory on the boundary of that space. In other words, the three-dimensional interior is a hologram projected from the two-dimensional boundary. This principle has been formalized in the ADS/CFT correspondence in string theory, which relates a gravitational theory in a higher dimensional space, anti-de Sitter space, to a quantum field theory on the lower dimensional boundary. While the ADS/CFT correspondence applies to specific, idealized scenarios, it has provided powerful insights into quantum gravity and has become a major research area in theoretical physics. Returning to observations, we must consider the challenges of imaging black holes directly. The Event Horizon Telescope achieved the first image of a black hole's shadow by coordinating observations from radio telescopes around the world, effectively creating an Earth-sized telescope. The resolution required is extraordinary. To resolve the event horizon of M87, which subtends an angle of about 40 micro-arcseconds on the sky, requires a telescope with a baseline of thousands of kilometers. The technique used is very long baseline interferometry, VLBI, where the signals from individual telescopes are combined to simulate a much larger aperture. The data from each telescope is time-stamped using atomic clocks and later correlated in a supercomputer to reconstruct an image. The process is complex, requiring exquisite timing, sophisticated calibration, and advanced algorithms to convert the sparse interferometric data into an image. The resulting images are not photographs, but reconstructions based on models and data fitting. Nonetheless, they provide a direct view of the environment of a black hole, confirming the presence of the shadow and the structure of the accretion flow. The detection of gravitational waves has provided direct confirmation that black holes merge. Before LIGO, the existence of binary black holes was inferred indirectly, but now we have heard the unmistakable signature of two black holes spiraling together and coalescing. The first detection, GW 150914, involved two black holes of approximately 36 and 29 solar masses merging to form a black hole of about 62 solar masses. The missing three solar masses were radiated away as gravitational waves, an amount of energy equivalent to the mass energy of three suns, released in a fraction of a second. This event occurred over 1 billion light years away, and the ripples in spacetime, though minute by the time they reached Earth, were detectable by LIGO's exquisitely sensitive interferometers. Since that first detection, dozens more have been recorded, revealing a population of black holes that was previously hidden. Some of these black holes are more massive than expected from standard stellar evolution, suggesting that either stellar models need revision or that these black holes formed through alternative channels, such as hierarchical mergers in dense clusters. The concept of the photon sphere, which we touched upon earlier, deserves further exploration. At one point, 5 times the Schwarzschild radius for a non-rotating black hole, photons can orbit in circular paths. This is an unstable orbit. Any slight perturbation sends the photons either inward to the event horizon or outward to infinity. For a rotating black hole, the situation is more complex, with the photon sphere modified by frame dragging. There exist prograde orbits in the direction of the black hole's rotation, and retrograde orbits against the rotation, with different radii. The photon sphere is the boundary of the black hole's shadow as seen from infinity. Light emitted from inside the photon sphere cannot escape. Light from outside can. The images produced by the Event Horizon Telescope show a bright ring corresponding to photons that have orbited the black hole multiple times before reaching us. This creates a series of nested rings, each fainter than the last, corresponding to photons that have made 1, 2, 3, or more orbits. Observing these subrings with higher resolution would provide even more detailed tests of general relativity and could constrain alternative theories of gravity. Black holes are often described as cosmic vacuum cleaners, sucking in everything around them. This is a misconception. In reality, black holes are no more sucking than any other gravitational source. If the Sun were suddenly replaced by a black hole of equal mass, the Earth would continue to orbit as before. It would not be sucked in. The gravitational influence at a given distance depends only on the mass, not on whether that mass is a star, a planet, or a black hole. What makes black holes unique is not their gravitational pull at a distance, but the fact that they have an event horizon. Once something crosses that threshold, it is lost. But to reach the event horizon, an object must venture extremely close. Most matter in the vicinity of a black hole orbits at safe distances, just as planets orbit stars. It is only when friction in an accretion disk or gravitational perturbations cause matter to lose energy and angular momentum that it spirals inward toward the point of no return. This process is not instantaneous. It can take thousands or millions of years for matter to migrate from the outer regions of an accretion disk to the inner edge and finally plunge through the horizon. The physics of accretion disks is rich and complex. These disks are not solid objects, but rather collections of particles, atoms, and magnetic fields, each element following its own Keplerian orbit, modified by pressure, magnetic forces, and viscosity. Viscosity, in this context, is not the familiar molecular viscosity of fluids, but an effective viscosity generated by turbulence. The magnetorotational instability mentioned earlier is the primary driver of this turbulence. Without it, accretion would proceed very slowly, as there would be no efficient mechanism to transport angular momentum outward. With it, the disk becomes a dynamic, chaotic environment where magnetic fields are continuously amplified, twisted, and reconnected. This turbulence heats the disk, causes it to radiate, and allows matter to spiral inward. The temperature of the disk varies with radius. Close to the black hole, where the orbital velocity is highest and the gravitational energy release is greatest, the disk is hottest, emitting X-rays and ultraviolet light. Further out, the disk is cooler, emitting optical and infrared light. By observing the spectrum of an accretion disk across multiple wavelengths, astronomers can map its temperature structure and infer its physical properties. The jets launched by black holes are among the most spectacular phenomena in the universe. These narrow beams of plasma travel at speeds close to that of light, extending for distances that can exceed the size of the host galaxy. The energy carried by the jets is enormous, capable of inflating vast cavities in the surrounding intergalactic medium. In radio observations, we see these cavities as bubbles of low-density, high-energy particles, outlined by the synchrotron radiation they emit. The jets are remarkably collimated, remaining narrow over enormous distances. This collimation is thought to be maintained by magnetic fields that thread the jet and confine the plasma. As the jet travels through space, it can interact with the ambient medium, shocking and heating the gas. When the jet eventually slows down and dissipates, it deposits its energy into the surroundings, a process that can influence the formation of stars and the evolution of the galaxy. The study of jets involves radio astronomy, X-ray observations of shocked gas, and optical spectroscopy of emission lines. High-resolution imaging with radio interferometers has revealed the internal structure of jets, showing knots and filaments that likely correspond to shock fronts and magnetic instabilities. Returning to the information paradox, recent developments suggest possible resolutions. One proposal involves the concept of soft hair. In classical general relativity, black holes have no hair. They are characterized only by mass, spin, and charge. But in quantum field theory, there are additional low-energy degrees of freedom associated with the horizon, called soft modes. These could encode information about the infalling matter, providing a way for information to be preserved without violating the no-hair theorem. Another proposal is that information escapes in subtle correlations between Hawking radiation quanta, correlations that become apparent only when one considers the quantum entanglement between successive emissions. A more radical idea is that the smooth horizon is an approximation, and that at the quantum level, the horizon is a highly energetic, turbulent region, a firewall that destroys infalling information in a way that is consistent with quantum mechanics, but violates the equivalence principle. This idea is controversial and has not gained universal acceptance, but it has stimulated a great deal of theoretical work. Yet another line of thought involves the holographic principle more directly, suggesting that the information is never truly inside the black hole, but is always encoded on the horizon in a form that is inaccessible to classical observers, but present in the quantum description. These debates are ongoing, and they touch on the deepest questions in theoretical physics: the nature of space-time, the meaning of information, and the unification of quantum mechanics and gravity. Let us consider the role of black holes in the chemical evolution of the universe. When massive stars explode as supernovae, they produce and disperse heavy elements, carbon, oxygen, iron, and others, into the interstellar medium. These elements are the building blocks of planets and life. But if a massive star's core collapses directly to a black hole, the supernova explosion may be weak or absent, and much of the heavy element production may fall into the black hole, lost to the universe. This is called a failed supernova, or a direct collapse. Observations of supernova rates and the properties of massive stars suggest that failed supernovae may be common, which has implications for the abundance of heavy elements in the universe. On the other hand, supermassive black holes, through their jets and winds, can eject material from galaxies, enriching the intergalactic medium with metals. This material can later be incorporated into new generations of stars in other galaxies. Thus, black holes play a dual role. They can sequester heavy elements, removing them from circulation, but they can also redistribute them across vast distances, seeding the cosmos with the products of stellar nucleosynthesis. We must also address the concept of black hole thermodynamics in greater detail. The temperature of a black hole, according to Hawking, is inversely proportional to its mass. For a solar mass black hole, the temperature is about 1/10 millionth of a Kelvin. For a supermassive black hole, it is even colder, far below the temperature of the cosmic microwave background. This means that such black holes are colder than their surroundings and will absorb more energy from the environment than they emit, causing them to grow. Only in the far future, when the universe has cooled below the temperature of even the largest black holes, will they begin to lose mass through Hawking radiation. The entropy of a black hole, proportional to the area of its event horizon, is enormous. A solar mass black hole has an entropy vastly exceeding that of the Sun itself. This high entropy is one reason why black holes are considered the ultimate repositories of disorder. When matter with relatively low entropy falls into a black hole, the total entropy of the universe increases dramatically, in accordance with the second law of thermodynamics. The study of black hole thermodynamics has revealed deep connections between gravity, quantum mechanics, statistical mechanics, and information theory, and it remains a fertile ground for theoretical exploration. The interior of a black hole, beyond the event horizon, is a realm of speculation and theoretical exploration. According to general relativity, an infalling observer would experience a finite proper time from crossing the horizon to reaching the singularity. For a stellar mass black hole, this time is a fraction of a second. The observer would not see the exterior universe frozen. Instead, due to the extreme curvature, they would see the outside universe blue shifted and sped up. In principle, if they looked back, they could see the entire future history of the universe flash before their eyes in the final moments. However, practical considerations, such as the intense tidal forces and the breakdown of spacetime near the singularity, would make such observations impossible. For a rotating black hole, the interior structure is more complex, with an inner horizon and a ring singularity rather than a point singularity. The region beyond the inner horizon might contain exotic structures, but these are likely unstable and may not correspond to physical reality. The truth is, we do not know what happens inside a black hole. Our equations break down, and without a theory of quantum gravity, we cannot make reliable predictions. This ignorance is not a failure of science, but a frontier, a signpost indicating where new physics must be discovered. Black holes may also serve as natural laboratories for testing the limits of quantum mechanics. The extreme conditions near the event horizon and singularity probe regimes where quantum effects and gravitational effects are both strong. In ordinary circumstances, quantum mechanics governs the very small, and gravity governs the very large, and the two realms rarely overlap. But near a black hole, they must both be considered. The phenomenon of Hawking radiation itself is a quantum effect in a strong gravitational field. The fact that black holes have a temperature and radiate implies that they obey thermodynamic laws, which are fundamentally statistical. This suggests that black holes have microstates, specific quantum configurations that correspond to a given macroscopic black hole. Counting these microstates to reproduce the Bekenstein-Hawking entropy has been a major achievement of string theory, at least for certain classes of black holes. If string theory is correct, black holes are not truly featureless, but are incredibly complex objects at the quantum level, composed of strings and branes in higher dimensional spaces. However, these ideas remain theoretical as we currently lack experimental access to the Planck scale where such effects would be manifest. We should also consider the observational prospects for the future. The next generation of telescopes and detectors promises to revolutionize black hole science. The James Webb Space Telescope, with its infrared capabilities, can peer through dust to observe the centers of galaxies, potentially detecting supermassive black holes in the early universe. Next-generation gravitational wave detectors will be sensitive to lower frequencies, allowing the detection of supermassive black hole mergers that occur when galaxies collide. The Square Kilometer Array, a radio telescope currently under construction, will map the distribution of neutral hydrogen across the universe, tracing the large-scale structure and the influence of black holes on their environments. Advances in X-ray spectroscopy will allow finer measurements of the innermost regions of accretion disks, probing the space-time geometry just outside the event horizon. The Event Horizon Telescope is expanding, adding new sites to improve resolution and enable imaging of more black holes. Future space-based missions may include an even larger interferometer, capable of resolving the shadows of smaller black holes, or imaging the dynamic processes around black holes in exquisite detail. The study of black holes is inherently interdisciplinary, drawing on physics, astronomy, mathematics, and even philosophy. It requires an understanding of general relativity, quantum field theory, thermodynamics, fluid dynamics, plasma physics, and high-energy astrophysics. It also demands sophisticated computational tools, as the equations governing black holes and their environments are too complex to solve analytically. Numerical relativity, the art of solving Einstein's equations on supercomputers, has made tremendous strides in recent decades, enabling the simulation of black hole mergers, the propagation of gravitational waves, and the dynamics of accretion disks and jets. These simulations have been essential for interpreting the data from LIGO, the EHT, and other observatories. They allow us to test theoretical predictions against observations and to explore scenarios that are inaccessible to direct observation. As computational power continues to grow, simulations will become ever more detailed and realistic, capturing the multi-scale, multi-physics nature of black hole environments. Let us delve deeper into the concept of gravitational redshift and time dilation. As light climbs out of a gravitational well, it loses energy, which manifests as an increase in wavelength, a redshift. For light emitted near the event horizon of a black hole, this gravitational redshift becomes extreme. Photons emitted from the innermost stable circular orbit can be redshifted by factors of 2 or more, shifting X-ray photons into the ultraviolet or even visible range by the time they reach a distant observer. This effect must be accounted for when interpreting the spectra of accretion disks. Time dilation is closely related. A clock near a black hole runs slower than a clock far away. If two observers synchronize their watches and one descends toward the black hole while the other remains at a safe distance, the descending observer's watch will lag behind. This is not an illusion or a trick of perception. It is a real physical effect arising from the curvature of space-time. For a spacecraft hovering just above the event horizon, time passes so slowly relative to the rest of the universe that minutes for the crew could correspond to years for those far away. This has been dramatized in science fiction, but it is grounded in rigorous physics. It is a consequence of the equivalence principle and the structure of spacetime as described by general relativity. The interaction between black holes and dark matter is another area of active research. Dark matter, which constitutes most of the matter in the universe, does not emit or absorb light, but it does exert gravitational influence. It is thought to form halos around galaxies, providing the gravitational scaffolding that holds them together. Black holes, as massive objects, can capture and accumulate dark matter. Over time, a black hole might build up a dense spike of dark matter in its vicinity. This spike could enhance the rate of dark matter annihilation if dark matter particles are their own antiparticles, leading to detectable signals in gamma rays or other high-energy particles. Some theories propose that black holes themselves could be made of dark matter in a certain sense, or that dark matter halos could collapse to form black holes under the right conditions. Observational searches for these signatures are ongoing, using space-based telescopes like Fermi and ground-based gamma-ray observatories. So far, no definitive signal has been found, but the searches continue, refining our understanding of both black holes and dark matter. Black holes also provide a natural explanation for some of the most extreme astrophysical phenomena. Ultraluminous X-ray sources, or ULXS, are objects that emit X-rays at luminosities exceeding the Eddington limit for stellar mass black holes. The Eddington limit is the maximum luminosity that a stably accreting object can achieve. Beyond this, radiation pressure would blow away the infalling material, halting accretion. ULXS were initially puzzling, but it is now thought that they are either intermediate mass black holes accreting at moderate rates, or stellar mass black holes accreting at super Eddington rates through beamed or geometrically thick accretion flows. Distinguishing between these scenarios requires detailed spectroscopic and timing analysis. Similarly, gamma-ray bursts, the most energetic explosions observed since the Big Bang, are thought to be powered by black holes. The long-duration gamma-ray bursts are associated with the collapse of massive stars, likely forming a black hole, which then drives a relativistic jet that punches through the stellar envelope. The short-duration bursts are believed to result from the merger of two neutron stars, which may also form a black hole. In both cases, the black hole is the central engine, converting gravitational energy into the intense radiation and particle beams that we observe. The question of what happens to information that falls into a black hole connects to the broader question of the nature of time and the arrow of thermodynamics. In quantum mechanics, the fundamental laws are time symmetric. They work equally well forward or backward in time. But in thermodynamics, there is a clear arrow of time. Entropy increases. Black holes, with their vast entropy and their one-way horizons, seem to embody this arrow in the starkest way. Once something falls in, it cannot come out. The process is irreversible. Yet, if Hawking radiation carries away information, even in subtle, encoded form, then perhaps the process is not truly irreversible in a quantum sense. The information might be scrambled and hidden, but not destroyed. This would preserve the unitarity of quantum mechanics, the principle that information is conserved. Resolving this tension requires a deeper understanding of how quantum information behaves in curved spacetime and what the microstates of a black hole actually are. It is a problem that sits at the intersection of quantum information theory, general relativity, and statistical mechanics, and it has driven much of the theoretical work in quantum gravity over the past few decades. We should also consider black holes in the context of modified theories of gravity. General relativity has been tested extensively and has passed every test with flying colors. However, it is not the only possible theory of gravity. There are alternative theories that modify Einstein's equations in various ways, either to address theoretical issues, like the singularities in black holes, or to explain cosmological observations, like dark energy and the accelerated expansion of the universe, without invoking new forms of matter or energy. Some of these theories predict deviations from general relativity in strong field regimes, such as near black holes. For example, scalar tensor theories introduce an additional scalar field that couples to gravity, potentially altering the properties of black holes. In such theories, black holes might have scalar hair, violating the no-hair theorem. Observations of black hole shadows, gravitational waves, and the motion of matter near black holes can test these alternative theories. So far, no deviations from general relativity have been detected, placing stringent constraints on modifications to gravity. But the search continues, as any confirmed deviation would be revolutionary, pointing to new physics beyond Einstein's theory.